Every moment of your waking life, you experience the world through a subjective lens, a private inner theater where sensations, thoughts, and emotions unfold in a way that feels unmistakably yours and inaccessible to anyone else. Yet despite centuries of neuroscience, philosophy, and psychology, we remain fundamentally unable to explain how this happens or why it happens at all. You see the color red, feel the warmth of sunlight on your skin, and experience the bittersweet ache of nostalgia. But when neuroscientists scan your brain during these moments, they observe only electrical impulses and chemical reactions flowing between billions of neurons in patterns that seem no different in principle from the computational processes occurring in a sophisticated machine. The hard problem of consciousness, as philosophers call it, asks not merely how the brain processes information, a question that seems answerable through continued scientific investigation, but rather how and why physical processes give rise to subjective experience itself, to the felt quality of what it is like to be you, rather than merely behaving as though you understand the world. The mechanisms underlying consciousness appear to involve the integration of information across different brain regions, the interplay between the thalamus and cortex, the mysterious role of neural oscillations and synchronized firing patterns, and yet understanding these mechanisms does nothing to explain the explanatory gap between the objective facts of brain function and the subjective reality of inner experience. We have normalized this profound mystery by relegating it to the category of inevitable ignorance, by telling ourselves that perhaps consciousness is simply an emergent property of complex systems, or that it represents information integration reaching a critical threshold, or that the question itself contains a conceptual confusion that will dissolve once we frame the problem correctly. But these proposed solutions often feel more like philosophical repositioning than genuine explanations. Ways of making peace with our inability to bridge the chasm between what we can measure in a laboratory and what we know with absolute certainty exists within our own minds, leaving consciousness as one of the deepest and most persistent mysteries at the intersection of science, philosophy, and human experience. Yet perhaps this very mystery reveals something essential, that consciousness cannot be fully captured by the methods we have devised to study it, that the observer and the observed remain entangled in a way that resists the clean separation required by objective science, suggesting that understanding consciousness may ultimately require not just better instruments and theories, but a fundamental expansion of what we consider valid knowledge. Imagine looking at the cosmos and discovering that everything you can see, every star, every galaxy, every speck of dust illuminated by light, comprises only about 15% of all the matter in the universe, while the remaining 85% remains completely invisible and undetectable by any conventional means, a phenomenon that astronomers and physicists have termed dark matter, which represents perhaps the most profound mystery in modern science because despite decades of intensive research, billions of dollars in funding, and the construction of increasingly sophisticated detection equipment, we still cannot definitively answer the fundamental question of what dark matter actually is. The evidence for dark matter's existence is overwhelmingly compelling and rooted in observable astronomical phenomena that cannot be explained through conventional physics. As when astronomers measure the rotational speeds of galaxies, they find that the outer regions spin far too quickly to be held together by the gravitational pull of visible matter alone. And gravitational lensing observations reveal that massive invisible structures bend and distort light from distant objects in ways that require the presence of substantially more matter than we can account for through telescopes and instruments that detect electromagnetic radiation. Scientists have proposed numerous candidates for dark matter's identity, including weakly interacting massive particles, often abbreviated as WIMPs, which would be exotic particles produced during the Big Bang and left over in abundance throughout the universe, primordial black holes that formed in the early universe's extreme conditions, or axions, theoretical subatomic particles that would interact only very weakly with ordinary matter and radiation. Yet despite constructing extraordinarily sensitive detectors deep underground where cosmic ray interference is minimized, and despite colliding particles at energies never before achieved in laboratories, these hypothetical dark matter particles have consistently eluded direct detection, remaining phantom-like in their elusive nature. The psychological mechanism underlying our persistent inability to solve this mystery involves the profound disconnect between mathematical prediction and physical observation. as our theoretical models predict with remarkable precision that dark matter must constitute most of the universe's mass. Yet our experimental apparatus cannot produce convincing evidence of what it actually is, creating a cognitive dissonance that persists in the scientific community. Where researchers have become accustomed to operating within this paradoxical framework, publishing thousands of papers each year exploring speculative candidates without breakthrough discoveries, and the mystery endures because. In the late 1990s, astronomers made an observation that fundamentally challenged our understanding of the universe's behavior, discovering that the expansion of space itself was not slowing down as gravity would suggest, but rather accelerating at an ever-increasing rate, as though some invisible force was pushing all galaxies away from one another with growing intensity. This mysterious phenomenon accounts for approximately 68% of the total mass and energy content of the entire universe. Yet despite being the dominant component of reality itself, we understand almost nothing about what it actually is or how it functions at a fundamental level. The universe is expanding faster now than it was billions of years ago, which means that whatever is driving this acceleration is becoming more powerful relative to gravity as time passes. And this observation stands as one of the most profound mysteries in modern physics, because it suggests that the vast majority of our cosmos is composed of something we cannot see, cannot touch, and cannot adequately explain through any of our current theoretical frameworks. Scientists have proposed numerous hypotheses to account for dark energy, ranging from the cosmological constant originally suggested by Einstein, which posits a uniform energy density throughout all of space, to more exotic ideas involving dynamical fields that change over time or modifications to the laws of gravity itself on the largest scales. Despite decades of intense investigation and increasingly sophisticated observations from space telescopes and ground-based instruments, we remain fundamentally unable to determine whether dark energy is a property of space itself, a new type of particle or field we have yet to discover, or perhaps evidence that our understanding of gravity breaks down at cosmic distances. What persists is our acceptance of this profound ignorance, our normalization of the fact that we have cataloged and named something we cannot comprehend, assigning it a placeholder term, and moving forward with our research knowing that the answer to one of the deepest questions in existence remains shrouded in mystery, waiting somewhere in the darkness between the stars. Yet this very darkness has become fertile ground for discovery. The search for dark energy's true nature has spawned entirely new fields of investigation, from quantum vacuum fluctuations to multidimensional theories, each representing humanity's persistent attempt to illuminate what may ultimately prove to be the universe's most fundamental secret. Perhaps most humbling is that dark energy may represent not a gap in our knowledge, but a fundamental limit to what can ever be known, a boundary where the universe itself becomes opaque to human inquiry, forcing us to confront the possibility T. Among the most profound mysteries that science continues to grapple with is the question of how life itself began on Earth, a puzzle that sits at the intersection of chemistry, biology, and physics, and one that has eluded definitive answers despite centuries of investigation and increasingly sophisticated experimental methods. We know that approximately 3.8 billion years ago, the early Earth possessed an atmosphere fundamentally different from today, containing methane, ammonia, hydrogen, and water vapor, with oceans that were warm and rich with dissolved minerals and organic compounds. Yet the precise mechanism by which non-living chemical matter organized itself into self-replicating systems remains enigmatic and contested among researchers. The prevailing hypothesis, known as abiogenesis, suggests that simple organic molecules spontaneously assembled through natural chemical processes, possibly catalyzed by energy from lightning, ultraviolet radiation, or thermal vents on the ocean floor, eventually forming RNA or DNA-like molecules capable of directing their own replication and metabolism. Yet despite decades of laboratory experiments recreating primordial conditions, from the famous Miller-Urey experiment to modern efforts synthesizing nucleotides and proteins in chemically plausible scenarios, we have never successfully demonstrated the complete transition from lifeless chemistry to living systems in a controlled setting, leaving a significant explanatory gap that haunts the theory. The psychological mechanism underlying our acceptance of abiogenesis, despite this gap, appears rooted in logical deduction. If life exists and life emerged on Earth, then non-biological chemistry must have somehow produced it, making the hypothesis logically inevitable regardless of empirical verification. Yet we have normalized incomplete understanding here, treating abiogenesis as established fact in educational contexts, while the actual mechanism remains speculative. And this normalization persists because the alternative explanations, whether divine creation or panspermia, invoke factors outside the scope of scientific methodology, leaving us in an unusual position where we have accepted as probable the very thing we cannot yet demonstrate. Suspended in intellectual patience, while awaiting the evidence that might finally resolve this deepest of biological mysteries. Some researchers now explore alternative frameworks, such as the RNA world hypothesis, suggesting that RNA preceded DNA as life's first genetic molecule, or the concept of metabolic first pathways, where chemical networks self-organized before replication emerged, each offering distinct windows into how complexity might have crystallized from simplicity, though each remains similarly incomplete in its explanatory power. Consider the sheer mathematical probability that we should encounter extraterrestrial life in our universe, a calculation so compelling that it formed the basis of what physicists call the Fermi paradox, named after the brilliant nuclear scientist Enrico Fermi, who posed a deceptively simple question during a lunch conversation in 1950. If the universe contains billions of galaxies, each with billions of stars, and if even a small percentage of those stars harbor planets capable of supporting life, then where is everybody? The numbers suggest that intelligent civilizations should exist throughout the cosmos in such abundance that we should detect their radio signals, observe their megastructures, or witness evidence of their expansion across the galaxy. Yet our telescopes reveal only silence, an absolute and profound silence that contradicts every reasonable expectation based on probability and scale. The psychological mechanism underlying our continued puzzlement about this paradox stems from the cognitive dissonance between two seemingly irrefutable truths. On one hand, the universe appears incomprehensibly vast and ancient, offering countless opportunities for life to emerge independently in different locations. And on the other hand, we see no convincing evidence of any civilization besides our own, creating a tension between mathematical inevitability and observable reality that our minds struggle to reconcile. We have proposed numerous explanations ranging from the sobering Great Filter hypothesis, which suggests that some catastrophic evolutionary bottleneck prevents nearly all civilizations from reaching technological maturity and spacefaring capability, to the comforting zoo hypothesis, which proposes that advanced extraterrestrial beings deliberately avoid contact with younger species, observing us from a distance like scientists studying specimens in a controlled environment. Yet despite decades of serious scientific inquiry, despite our most sophisticated attempts to detect signals through programs like SETI, and despite our growing ability to identify potentially habitable exoplanets orbiting distant stars, the fundamental mystery persists in an almost unsettling way, suggesting that either our understanding of life's prevalence in the universe is dramatically wrong, or intelligence itself follows patterns of emergence and extinction that we have yet to comprehend, leaving us suspended in an eternal puzzle where the absence of evidence continues to constitute evidence of absence, or perhaps something far stranger that dwells beyond the boundaries of our current understanding. One possibility that has gained traction in recent years is the observation that our own existence may be statistically improbable, suggesting we occupy a rare corner of a universe far more hostile to L. Deep within the realm of quantum mechanics exists one of the most perplexing paradoxes in all of science, a puzzle that has confounded physicists for nearly a century and remains fundamentally unresolved despite our tremendous technological progress. This is the measurement problem, and it strikes at the very heart of how reality itself functions at the smallest scales. When scientists observe subatomic particles like electrons or photons, something extraordinary and deeply troubling occurs. The act of measurement fundamentally changes the behavior of what is being measured. Before observation, quantum theory tells us that particles exist in what is called a superposition, a ghostly state where they simultaneously occupy multiple positions, spin in multiple directions, or possess multiple energy states all at once. These particles are described by a mathematical function called a wave function, which represents all possible states the particle could be in, each with its own probability. However, the moment a scientist attempts to measure or observe the particle, something remarkable happens. The wave function collapses instantly into a single definite state, and the particle suddenly appears to have just one position, one spin direction, or one energy level. The strange part is that before measurement, there was no fact of the matter about which state the particle was really in. The measurement itself somehow forces reality to make a decision. This creates an immediate philosophical crisis. If the act of observation creates the reality we observe, what exactly is happening? Are particles truly in superposition until we look at them, or does the superposition represent only our incomplete knowledge about them? Is consciousness involved in collapsing the wave function, or is measurement defined more broadly as any physical interaction that extracts information? Different interpretations of quantum mechanics offer wildly different answers. The Copenhagen interpretation suggests that particles genuinely do not have definite properties until measured, and measurement is a fundamental, irreducible feature of nature. The many worlds interpretation proposes that every measurement causes reality to split into multiple branches, with each possible outcome occurring in a different universe. The pilot wave theory suggests hidden variables guide particles along predetermined paths. And yet, despite having multiple competing theories, none of them fully resolves the measurement problem in a way that satisfies the entire scientific community. What makes this mystery so persistent is that it remains almost entirely invisible in practical applications. One of the deepest questions that confronts cosmologists, philosophers, and curious minds alike is the question of what existed before the Big Bang, that singular moment approximately 13.8 billion years ago, when our universe began its violent expansion from an infinitely dense point. The challenge with this question is not merely that we lack observational data or that our telescopes cannot peer backward through time far enough to witness those primordial moments, but rather that the very framework of causality and time itself appears to break down at the threshold of the Big Bang, making the question itself potentially meaningless in ways that deeply trouble our intuitions about how reality should function. Scientists and thinkers have proposed numerous possibilities to address this conceptual void. Perhaps there was another universe before ours, a cyclical cosmos that eternally expands and contracts, birthing new universes in endless succession. Perhaps time itself did not exist before the Big Bang, and therefore the question of what came before is like asking what is north of the North Pole. Perhaps our universe is merely one among infinite others, existing in a vast cosmic foam where pocket universes constantly nucleate and expand within some larger multiverse framework that we may never observe or understand. What makes this mystery particularly psychologically fascinating is how our minds demand an answer despite the possibility that no sensible answer can exist within our current mathematical and philosophical frameworks, revealing a deep human need to ground existence in some prior cause, some originating force that explains how something came from nothing at all. We have normalized the existence of this profound mystery by categorizing it as beyond our reach, by telling ourselves that such questions belong to philosophy rather than science. Yet the boundary between these disciplines continues to blur as theoretical physics ventures ever deeper into questions about the nature of reality itself, time, causality, and the very possibility of existence before existence began. Perhaps the most humbling aspect of this inquiry is that the answer, if one exists, may fundamentally exceed the capacity of human cognition itself, not because we lack sufficient data or computational power, but because our brains evolved to navigate a universe where causality and time always flow forward, leaving us neurologically unprepared to comprehend a reality where these scaffolding principles simply do not apply. In this sense, the question of what preceded the Big Bang may be less a scientific puzzle awaiting solution, and more a fundamental limit sign marking the edge of what any finite mind, constrained by the laws of its own universe, can ever hope to comprehend. Imagine sitting in a quiet room, observing the color red on a screen before you, and ask yourself a deceptively simple question. Why does red look the way it looks to you, and not some other way entirely? This is the essence of the hard problem of consciousness, a question that has puzzled philosophers, neuroscientists, and thinkers for centuries without resolution. You can measure the wavelength of light, map the neural pathways in your brain that respond to that wavelength, document every chemical reaction and electrical impulse that occurs when you perceive redness, and yet none of this explains why the experience of seeing red feels like something specific to you. This subjective quality of experience, the felt sense of what something is like from the inside, is called qualia, and it remains perhaps the most perplexing mystery in all of science and philosophy. When you taste chocolate, feel pain, hear a beautiful melody, or experience the warmth of sunlight on your skin, your brain is undoubtedly doing something measurable and physical, yet the question persists. How do these objective physical processes give rise to subjective inner experience? Scientists can tell you which neurons fire during color perception, which neurotransmitters are involved, how your visual cortex processes information. But explaining the mechanism of consciousness is fundamentally different from explaining why that mechanism produces the particular felt quality of redness rather than blueness or something entirely unknown. This disconnect between our ability to explain brain function and our utter inability to bridge the explanatory gap to subjective experience creates a unique puzzle that resists the standard scientific method. Despite decades of neuroscientific advancement and increasingly sophisticated brain imaging technology, we have not moved significantly closer to answering why physical processes in 3 pounds of biological tissue should produce consciousness at all, making the hard problem not merely unsolved, but seemingly unsolvable through conventional approaches. Some philosophers propose that consciousness might be fundamentally irreducible to physical explanation, that no amount of brain mapping will ever bridge this gap because subjective experience operates on a different plane of reality entirely. Others suggest we may be asking the wrong question altogether, and that future generations might look back on our puzzlement with the same bemused recognition we reserve for ancient scholars debating how many angels could dance on a pinhead. Yet until that moment of clarity arrives, the hard problem remains a humbling reminder that consciousness itself, the very thing enabling us to ponder these questions, may be the one phenomenon that forever eludes our complete understanding. Imagine standing in a room watching a cup of coffee cooling on a table, steam rising into the air, the liquid gradually reaching room temperature. Now imagine reversing that scene in your mind, the cold coffee spontaneously heating up, drawing thermal energy from the surrounding air, steam condensing back into the cup in perfect reverse. You immediately recognize this reversal as impossible, yet if you examine the fundamental laws of physics governing individual particles, you would find that nearly all of them work equally well forwards and backwards in time. This is the arrow of time, one of science's most profound mysteries. Why does time seem to flow in only one direction when the microscopic laws that underpin reality appear completely indifferent to temporal direction? The universe behaves as though it has a preferred direction, yet no one can adequately explain why this preference exists at the deepest level of physical law. When physicists observe particles colliding or electrons moving through space, the equations describing these interactions remain valid whether time moves forward or backward, suggesting that at the quantum level, the universe should be perfectly reversible. And yet macroscopic reality presents an unmistakable arrow, a clear sense that past and future are fundamentally different. We remember the past but not the future, causes precede effects, entropy increases, systems naturally progress toward disorder. Scientists have proposed various explanations. The thermodynamic arrow suggests that the second law of thermodynamics, which states that entropy must increase in closed systems, creates our sense of temporal direction. The psychological arrow emerges from our ability to remember prior events and our cognitive inability to remember future ones. The cosmological arrow connects to the expansion of the universe itself, yet somehow, despite decades of investigation and multiple competing theories, no unified explanation has gained universal acceptance. The mystery deepens when you consider that these arrows do not all point in the same direction in all circumstances, that at certain scales they seem to operate independently, and that quantum mechanics itself presents subtle ambiguities about temporal symmetry. We experience time as flowing in a single direction so completely that it shapes our entire understanding of causality, free will, and existence itself. Yet the mechanism generating this universal experience remains one of physics' most stubborn unsolved problems, suggesting that something fundamental about the nature of time continues to elude our understanding. Perhaps the most unsettling possibility is that time's arrow may not be a fundamental feature of reality at all, but rather an emergent property that only becomes apparent when countless particles interact. Imagine throwing a book into a black hole, watching it disappear beyond the event horizon, and then wondering what happens to all the information contained within those pages. This is the essence of the black hole information paradox, one of the most profound unsolved mysteries in theoretical physics that has challenged our fundamental understanding of the universe for decades. When Stephen Hawking discovered in the 1970s that black holes are not entirely black, but instead emit radiation due to quantum effects near the event horizon, he inadvertently created a crisis in physics. According to his calculations, this Hawking radiation would cause black holes to gradually evaporate and disappear completely from the universe, taking with them all the information about everything that had ever fallen into them. This presented a catastrophic problem because quantum mechanics, one of the two pillars of modern physics, strictly forbids information from being destroyed. The universe, according to quantum theory, must preserve all information in some form, yet black holes appeared to violate this fundamental principle by irreversibly erasing information from existence. The paradox deepens when you consider the implications for the very nature of reality itself. If information can be destroyed in black holes, then the reversibility of physical processes breaks down, and the entire mathematical framework upon which quantum mechanics is built would crumble. Physicists have proposed numerous solutions over the decades, from the idea that information might be encoded on the black hole's event horizon through something called the holographic principle, to suggestions that information might escape in subtle correlations within the Hawking radiation itself. Yet despite nearly 50 years of intense theoretical work involving some of the greatest minds in physics, no consensus solution has emerged. String theorists, quantum information specialists, and gravitational physicists continue to debate the issue, each with compelling arguments but without definitive proof. The black hole information paradox persists as a reminder that something fundamental about our understanding of quantum gravity remains incomplete, suggesting that the universe operates according to principles we have not yet discovered or fully comprehended. Perhaps the resolution will require us to fundamentally reimagine what we mean by information itself, or to reconcile quantum mechanics with general relativity in ways we haven't yet conceived, a challenge that may ultimately reshape our understanding of time, causality, and the very fabric of spacetime. Consider the possibility that our universe might not be the only one in existence, that beyond the edges of what we can observe and measure, there could be infinite other universes operating by different physical laws, populated by different versions of reality entirely. This concept, known as the multiverse theory, emerges from several legitimate branches of modern physics, particularly from quantum mechanics and cosmological models that suggest our Big Bang might not have been a singular event, but rather one bubble among countless others in an eternally inflating cosmic foam. The mathematical frameworks of string theory propose that there could be up to 10 to the 500th power possible universes, each with different fundamental constants and properties, while the many worlds interpretation of quantum mechanics suggests that every quantum event spawns new universes where all possible outcomes occur simultaneously. Scientists observe anomalies in the cosmic microwave background radiation that some argue could indicate collisions with neighboring universes, and the apparent fine-tuning of physical constants that allow life to exist seems less improbable if infinite universes exist with every possible configuration. Yet despite these compelling theoretical underpinnings, the multiverse remains fundamentally untestable and unobservable by definition, since anything beyond our cosmic horizon cannot send signals that reach us or be measured by our instruments, creating an unusual situation in physics where a hypothesis can be mathematically elegant and logically derived from accepted theories, yet remain forever beyond empirical verification. We have become comfortable with this paradox in modern theoretical physics, accepting multiverse concepts in academic circles despite their unfalsifiable nature, because they emerge naturally from equations we trust and solve genuine problems in our understanding of cosmic origins and quantum behavior, normalizing the existence of infinite undetectable realities as a serious scientific consideration rather than dismissing such ideas as pure speculation. The multiverse persists in scientific discourse not because we have found proof, but because the mathematics that describes our universe seems to point inexorably toward such conclusions, creating a strange modern situation where our most rigorous scientific methods lead us toward conclusions that transcend the very definition of what science can investigate. This tension between mathematical necessity and empirical impossibility reveals something profound about the nature of modern scientific inquiry itself, that our pursuit of truth has led us to a frontier where we must choose between abandoning elegant theoretical frameworks or accepting that reality may extend far beyond what we can ever know. Consider the fundamental constants that govern our universe, those seemingly arbitrary numbers that determine how atoms form, how stars burn, how galaxies spiral through the cosmic void. The strength of gravity, the electromagnetic force, the mass of electrons, the expansion rate of space itself, each of these values appears to be calibrated with extraordinary precision, as if tuned by some invisible hand to permit the existence of stars, planets, and ultimately life as we know it. This is the fine-tuning problem, one of the deepest mysteries at the intersection of physics and philosophy. Change any of these constants by even a fraction of a percent, and the universe becomes a barren wasteland where no complexity can emerge. Increase the strength of the strong nuclear force slightly, and nuclei become unstable, preventing the formation of heavy elements necessary for chemistry and biology. Decrease gravity by a tiny margin, and stars never ignite, leaving the cosmos cold and dark. Alter the ratio between the electromagnetic and strong forces, and molecules cannot form in the configurations required for life. The precision is genuinely staggering, comparable to firing a rifle bullet across the entire observable universe and hitting a target the size of a subatomic particle. Yet this extraordinary coincidence demands explanation. Why should the universe be fine-tuned for life when there is no apparent reason it should be? Scientists and philosophers have proposed various mechanisms to account for this improbability. The multiverse hypothesis suggests that countless universes exist with different physical constants, and we naturally find ourselves in one of the rare universes where conditions permit observers like ourselves to exist. The anthropic principle formalizes this reasoning, stating that we should expect to observe a universe compatible with our existence, simply because we could not observe any other kind. Some physicists argue that deeper mathematical principles or hidden symmetries might explain why the constants must take their particular values, suggesting that what appears fine-tuned might actually be inevitable. Others propose that consciousness itself plays a fundamental role in collapsing quantum possibilities into the specific physical laws we observe. Despite the profound nature of this mystery, it has become normalized within scientific discourse, accepted as a genuine puzzle rather than evidence demanding immediate philosophical revolution. We have grown accustomed to discussing the improbability without panic, treating fine-tuning as simply another frontier of physics awaiting explanation, much as previous generations accepted the mystery of gravity or radioactivity until deeper understanding emerged. One of the most profound mysteries in modern physics surrounds the possibility of traveling faster than light, a concept that Einstein's theory of special relativity established as fundamentally impossible, yet one that continues to captivate scientists, engineers, and dreamers alike who refuse to accept this cosmic speed limit as final. The historical context of this mystery begins with Einstein's equations, which demonstrated that as an object accelerates closer to the speed of light, its mass effectively increases, requiring exponentially more energy to push it further, so that reaching light speed would theoretically require infinite energy, making faster-than-light travel seemingly impossible by the very laws that govern our universe. However, in 1994, physicist Miguel Alcubierre proposed a mathematical solution to Einstein's field equations that suggested warping spacetime itself could allow a vessel to traverse vast distances faster than light could travel through normal space, without the spacecraft itself exceeding light speed relative to the space immediately around it, a concept that technically doesn't violate relativity because the light speed limit applies to objects moving through space, not to space itself. The psychological mechanism behind humanity's persistent fascination with faster-than-light travel stems from our inherent desire to transcend apparent limitations, and our historical pattern of dismissing the impossible until it becomes mundane, much as people once believed supersonic flight was physically impossible until the sound barrier was broken in 1947. The Alcubierre drive and similar proposals, while mathematically consistent with general relativity, require exotic matter with negative energy density, also called negative mass or dark energy, which has never been conclusively detected or understood, and which may require quantities far beyond anything theoretically available in the observable universe. We have normalized this mystery by compartmentalizing it into categories of pure theory and speculative science, treating faster-than-light travel as a distant dream rather than an insurmountable wall, allowing physicists to continue exploring these mathematical landscapes with the understanding that they may never translate into practical technology. Yet the very fact that Einstein's equations do not absolutely forbid such phenomena keeps the door perpetually ajar in our collective imagination. From wormholes that might connect distant regions of spacetime to quantum entanglement phenomena that seem to transmit information instantaneously across vast distances, physics continues to reveal nature's loopholes, suggesting that the universe itself may harbor secrets we have yet to fully comprehend or adequately interpret. On August 15, 1977, a radio astronomer named Jerry Ayman was reviewing data collected by the Big Ear Radio Telescope at Ohio State University when he noticed something that would puzzle scientists for decades to come: a series of radio signals that appeared to originate from deep space and exhibited characteristics that seemed remarkably consistent with what an extraterrestrial transmission might look like. A phenomenon so striking that Ayman circled the relevant data on the computer printout and wrote the word "wow" in the margin, a spontaneous expression of astonishment that would become the permanent name for one of science's most tantalizing mysteries. The signal arrived at a frequency of 1420 megahertz, the hydrogen line frequency that scientists had long theorized an advanced civilization might use for interstellar communication, and it displayed a strength pattern that suggested it came from a narrow beam rather than scattering across the sky like most natural radio sources, characteristics that made it appear fundamentally different from known celestial phenomena like pulsars or quasars. Yet when scientists attempted to locate the source again, conducting repeated observations of the same region of the sky, the signal never returned, vanishing as mysteriously as it had appeared, leaving behind only those 37 seconds of recorded data and the lingering question of what humanity had briefly glimpsed. The human mind has an intrinsic drive to organize chaotic information into meaningful patterns, and when we encounter something truly anomalous, something that does not fit neatly into our existing frameworks of understanding, we naturally gravitate toward the most dramatic explanations available to us, particularly when those explanations touch upon our deepest questions about our place in the universe and whether we are truly alone. The WOW signal arrived at precisely the right moment in human history when we had developed the technology to potentially detect such a message, but lacked the certainty to confirm it, creating a perfect vacuum for speculation and wonder to flourish. And the signal's very elusiveness only deepened its psychological grip on the popular imagination because it could never be definitively disproven or explained away. Decades have passed since that momentous August evening, and the scientific community has proposed various explanations ranging from an unusually strong terrestrial signal bounced off space debris to a previously unknown natural radio phenomenon. Yet none of these explanations have achieved universal acceptance or fully satisfied the curiosity they attempted to resolve. And perhaps this is precisely why the WOW signal endures so powerfully in our collective consciousness, because it represents. In October of 2017, astronomers detected something extraordinary passing through our solar system, a celestial object that would challenge our understanding of how the universe populates itself with visitors from distant stars. The object, named Oumuamua, which means scout or messenger in Hawaiian, arrived from interstellar space traveling at such tremendous velocity that it could only have originated from beyond our solar system, making it the first confirmed interstellar visitor ever recorded by human instruments. What makes Oumuamua so profoundly mysterious is not simply its origin, but rather its behavior and physical characteristics, which have resisted easy categorization and spawned numerous competing theories about what this strange wanderer truly is. Observations revealed that Oumuamua accelerates as it moves away from the sun in a manner that cannot be adequately explained by gravitational forces alone, suggesting that some additional force must be acting upon it, whether that force emerges from solar radiation pressure, outgassing, or something far more exotic still. The object appears elongated and tumbling through space, rotating erratically as it travels, and its reflectivity patterns suggest an unusual composition that does not perfectly match any known asteroid or comet type that scientists have cataloged from within our own solar system. Scientists have proposed explanations ranging from the conventional to the extraordinary, suggesting that Oumuamua might be a fragment ejected from a distant planetary system, a rogue comet composed largely of ice and dust, a piece of a solar sail propelled by technological means, or even a probe sent deliberately to observe our world, though each theory carries its own logical complications and gaps in evidence. The psychological mechanism underlying our fascination with Oumuamua relates to the profound human desire to explain the unknown through frameworks we can grasp. And when an object refuses to fit neatly into existing categories, we find ourselves compelled to generate increasingly elaborate hypotheses to resolve the discomfort of uncertainty. Despite years of observation and analysis by the world's most advanced astronomical instruments and brilliant scientific minds, Oumuamua continues to elude definitive explanation, remaining stubbornly enigmatic and resistant to consensus. A cosmic visitor that passes through our understanding without ever fully revealing what it is, leaving us to wonder whether we simply lack the tools to comprehend its true nature, or whether it possesses characteristics and origins genuinely beyond our current framework of knowledge. Among the most perplexing atmospheric phenomena ever reported by witnesses across centuries of observation stands the enigmatic manifestation known as ball lightning, a glowing orb of light that appears to move independently through the sky, sometimes during thunderstorms and occasionally in clear weather, defying conventional explanation and challenging our fundamental understanding of electromagnetic physics. These spheres, ranging in diameter from a few centimeters to several meters, have been described by credible observers as brilliantly luminous, often colored blue, white, or reddish, and capable of moving horizontally through the air at varying speeds, sometimes hovering motionless before suddenly accelerating or changing direction in ways that seem to contradict the laws of aerodynamics and electromagnetism that govern ordinary lightning. The phenomenon occurs rarely enough that controlled scientific observation remains virtually impossible, yet frequently enough that thousands of detailed accounts have accumulated from witnesses spanning multiple continents and centuries, each observer reporting strikingly similar characteristics that suggest a genuine physical process rather than hallucination or misidentification. The prevailing scientific theories attempting to explain ball lightning typically invoke exotic mechanisms involving plasma formation, where electrical energy ionizes atmospheric gases and somehow maintains itself within a stable, luminous structure that persists far longer than conventional lightning, which typically lasts only microseconds, whereas ball lightning reports describe phenomena lasting anywhere from several seconds to several minutes. Some researchers propose that ball lightning represents a self-contained plasma sphere held together by its own magnetic field. Others suggest it involves exotic chemical reactions between atmospheric constituents, and still others hypothesize mechanisms involving exotic matter or quantum effects. Yet none of these theories has achieved anything approaching consensus or definitive experimental validation. What persists most strikingly is the fundamental paradox that despite centuries of observations and modern scientific investigation, no laboratory has successfully and reproducibly created ball lightning under controlled conditions, leaving us in the peculiar position of acknowledging a phenomenon that countless reliable witnesses have observed, while simultaneously lacking any mechanism we can definitively prove generates it. A situation that forces us to contemplate how certain mysteries maintain their status as genuine scientific unknowns, even as our technological capabilities expand exponentially. The placebo effect represents one of the most perplexing phenomena in modern medicine, a genuine biological response that occurs when a person receives a treatment that contains no active therapeutic ingredient whatsoever, yet still experiences measurable improvement in their condition. Patients who take sugar pills while believing they are receiving real medication often report significant relief from pain, nausea, fatigue, and numerous other symptoms. And remarkably, brain imaging studies have confirmed that these improvements involve actual changes in neural activity and biochemical processes. In clinical trials across countless diseases and conditions, placebo treatments have been shown to activate the same neural pathways and trigger the release of the same neurochemicals as genuine pharmaceuticals, suggesting that the mind possesses an extraordinary power to literally heal the body through expectation alone. The mechanism appears to involve the patient's anticipation and belief in treatment effectiveness, which somehow communicates through the nervous system to produce tangible physiological changes, including reduced inflammation, altered pain perception, and even improvements in immune function. The brain seems capable of manufacturing its own medicine when properly convinced that medicine has been administered, creating endogenous opioids and other beneficial compounds through pure psychological expectation. What makes this phenomenon so scientifically troubling is that we have normalized its existence despite our inability to fully explain the causal pathway by which thought becomes biology, by which belief alters matter in such concrete and measurable ways. We continue to use placebos in medical research as control groups, yet we still cannot articulate precisely how a sugar pill convinces the immune system to fight infection more effectively, or how expectation literally dampens pain signals traveling through the spinal cord to the brain. The placebo effect persists as a fundamental mystery in neuroscience and medicine, a reminder that consciousness itself may possess capabilities we have yet to adequately understand or explain within our current scientific frameworks. This recognition has profound implications for how we conceptualize the relationship between mind and body, suggesting that the boundary between psychological and physical medicine may be far more permeable than traditional medical models have assumed, and that future therapeutic approaches might harness this mysterious connection more deliberately rather than merely controlling for it in research designs. Some researchers now propose that harnessing placebo mechanisms intentionally, through narrative reframing, ritual, and therapeutic alliance, could transform medicine into a more holistic discipline that treats PA. Every single night, your brain enters a state of profound activity while your body lies motionless, and during these hours of sleep, your mind generates elaborate narratives filled with impossible scenarios, forgotten people, and strange logic that seems to make perfect sense in the moment but dissolves the instant you wake. These dreams have fascinated humanity for thousands of years, appearing in ancient texts and spiritual traditions as messages from the divine, windows into the soul, or prophecies of the future. Yet despite centuries of scientific investigation, we still cannot definitively explain why we dream at all or what evolutionary purpose these nightly hallucinations actually serve. Researchers have proposed countless theories over the decades, suggesting that dreams might consolidate memories by replaying the day's experiences and integrating them into long-term storage. Or perhaps they serve as a kind of psychological rehearsal where the brain safely practices responses to threatening situations without any real-world consequences. Some neuroscientists argue that dreams are simply random neural noise, the brain's idle chatter as different regions fire chaotically during rapid eye movement sleep, while others contend that this apparent randomness actually masks sophisticated emotional processing and problem-solving mechanisms working beneath the surface of consciousness. The activation synthesis hypothesis proposes that the dreaming brain attempts to make sense of random signals generated during sleep, constructing narratives from whatever neural activity happens to occur, turning meaningless electrical impulses into the vivid storylines we experience. Yet despite decades of research using brain imaging, sleep laboratories, and psychological analysis, we have found no definitive answer, no clear proof that dreams serve any purpose at all, and remarkably, we continue to live comfortably with this profound ignorance about something that occupies roughly 6 years of an average human lifetime. We have normalized not knowing why a third of our existence is spent in this strange altered state, and we accept dream interpretation as either pure psychology or pure fantasy without ever truly understanding the mechanism driving these nocturnal experiences, continuing to wake each morning, forget our dreams, and return to them the next night in an endless cycle of mystery. Perhaps the greatest irony is that this mystery persists not because we lack the tools to study dreams, but because the very nature of consciousness makes dreams fundamentally difficult to examine. We can measure brain waves and observe neural firing patterns, yet the subjective experience of a dream, the feeling of flying or the emotion of loss, remains locked within the private theater of individual minds, accessible. Every single night, billions of humans around the world surrender consciousness and enter a state of profound vulnerability, lying motionless for hours while their brains perform functions we still do not fully understand. And despite decades of neuroscientific research and countless studies examining the architecture of sleep, we remain fundamentally uncertain about why this biological imperative exists at all. We know that sleep involves distinct stages, from light sleep to deep restorative sleep to rapid eye movement sleep where dreams occur. And we know that during these stages our brains consolidate memories, flush out metabolic waste products that accumulate during waking hours, repair cellular damage, and regulate hormones that control everything from hunger to mood to immune function. Yet none of these explanations fully accounts for why we need to lose consciousness entirely rather than simply resting while awake. The leading theories suggest that sleep serves multiple critical functions simultaneously. The glymphatic system, a network of channels in the brain, becomes dramatically more active during sleep and removes neurotoxic proteins like beta amyloid that accumulate throughout the day and are associated with neurodegeneration and Alzheimer's disease, while the consolidation of memories appears to require the specific neural activity patterns that only occur during sleep, particularly the replay and reorganization of experiences that transforms short-term memories into long-term storage. Yet what remains peculiar and somewhat paradoxical is that despite sleeping roughly one-third of our lives, we cannot explain precisely why evolution settled on such an extreme solution to these problems, why we could not accomplish memory consolidation while remaining conscious, or why we require such extended periods of helplessness when we could be gathering food, caring for offspring, or protecting ourselves from predators. The mystery deepens when we consider that the specific amount of sleep we require varies dramatically between individuals and species, that some creatures sleep with only half their brain at a time while remaining alert, and that humans are essentially alone in our need for such prolonged periods of complete unconsciousness, suggesting that whatever sleep does for us, it does something uniquely necessary for our particular kind of mind and biology that we have not yet fully articulated or understood. What we do know is that sleep deprivation produces catastrophic consequences: impaired cognition, emotional dysregulation, weakened immunity, and eventually death in extreme cases, suggesting that whatever sleep accomplishes is so fundamentally vital that our bodies will prioritize it above almost everything else, even when doing so puts us at risk, and this desperate biological in sea. Have you ever walked into a room, a restaurant, or a street you've never been to before, only to experience an overwhelming and inexplicable sensation that you have already lived through this exact moment in the past, that you have seen these specific objects arranged in precisely this way, heard these particular sounds, and felt this exact emotion before, even though you know with absolute certainty that this is your first time in this location? This phenomenon, known as déjà vu, from the French phrase meaning already seen, is one of the most common yet profoundly mysterious experiences that the human mind produces, affecting approximately 60 to 80% of people at least once in their lifetime, often multiple times, yet remaining almost entirely unexplained by modern neuroscience and psychology despite centuries of investigation and countless theoretical frameworks. The experience itself is remarkably consistent across cultures and individuals, a strange disconnection between what your conscious mind knows to be true and what your deeper cognitive systems seem to be insisting upon, a brief but vivid moment where your brain appears to misfire in a very specific and reproducible way. Several competing theories attempt to explain this phenomenon, with the hologram theory suggesting that our memories might be encoded in a manner similar to holograms, where any fragment might contain information about the whole, causing partial pattern matches to trigger false recognition of complete experiences, while the divided attention theory proposes that when your attention is divided between multiple stimuli during an initial encounter with something new, you fail to fully encode the experience into memory, but when you return to that place or situation with focused attention, your brain recognizes the patterns and creates the false impression of remembering something you never properly learned. Other researchers suggest that déjà vu might result from a momentary glitch in memory retrieval systems, where the neural pathways that mark an experience as familiar become activated before the actual memory content reaches conscious awareness, creating a genuine feeling of familiarity attached to entirely new information, essentially a timing error in the brain's multiple memory systems working slightly out of synchronization with one another. Yet despite these theories, despite the countless studies conducted in laboratories around the world, despite our increasingly sophisticated understanding of neurobiology and consciousness itself, déjà vu remains stubbornly resistant to complete explanation, a phenomenon that we have learned to describe and categorize, but still cannot fully understand or predict, a reminder that even in an age of advanced brain imaging and computational models of cognition, in the vast electromagnetic spectrum that surrounds our planet, astronomers have detected something genuinely puzzling. Brief, intense bursts of radio waves arriving from deep space, lasting only milliseconds yet releasing as much energy as our sun produces in entire days. And these phenomena, known as fast radio bursts or FRBs, first appeared in astronomical data around 2007, initially dismissed as mere instrumental errors or interference, until the scientific community was forced to acknowledge their authenticity as genuine cosmic events occurring far beyond our galactic neighborhood. What makes these bursts particularly enigmatic is their randomness and unpredictability, appearing without warning across different regions of the sky, and when astronomers attempt to trace their origins with telescopes and observational instruments, they encounter a frustrating absence of any obvious source, any detectable supernova remnants, any obvious stellar explosion, or any conventional astrophysical phenomenon that might adequately explain the sudden, violent release of such tremendous energy concentrated into such an impossibly brief timeframe. The human mind seeks patterns and causality in natural phenomena, and when faced with something as violent and energetic as a fast radio burst, our instinctive reasoning pulls us toward familiar explanations. Perhaps colliding neutron stars, or the catastrophic final moments of a dying star, or some exotic form of matter undergoing rapid transformation. Yet none of these conventional mechanisms entirely satisfies the observational data, and some bursts repeat at irregular intervals while others appear only once, suggesting that fast radio bursts might comprise multiple different classes of events with entirely separate origins and physical processes governing their behavior. The mystery deepens when we consider that the universe contains vast distances and immense timescales beyond human intuition, and within this cosmic framework, we have essentially only begun sampling an infinitesimal fraction of the sky with instruments sensitive enough to detect these elusive signals. And despite our rapid advances in radio astronomy and our growing catalog of documented fast radio bursts, their fundamental nature remains obscured, leaving us to contemplate whether we are witnessing the death throes of exotic stellar remnants, the signatures of advanced technologies operating on civilizational scales, or some entirely novel physics that challenges our current models of stellar evolution and electromagnetic phenomena. And perhaps this uncertainty itself reflects something profound about the limits of human knowledge when confronting a cosmos vastly older and more complex than our comprehension readily encompasses. When two particles become quantum entangled, they form a connection so profound that measuring one particle instantly influences the state of the other, regardless of the distance separating them, whether they are separated by millimeters or by the entire width of the observable universe. And yet, despite more than a century of experimental verification and countless technological applications built upon this phenomenon, physicists still cannot definitively explain why this happens or what mechanism allows information or correlation to propagate instantaneously across space in a way that seems to violate everything we understand about the cosmic speed limit established by Einstein's theory of relativity. The particles do not send signals to one another in any conventional sense, and no usable information can be transmitted faster than light through entanglement. Yet the correlation is undeniably real and has been tested to extraordinary precision through Bell tests and other sophisticated experiments that consistently demonstrate this spooky action at a distance, as Einstein himself famously called it with considerable skepticism. The deeper mystery lies not in whether entanglement occurs, but in the fundamental nature of reality that permits it to occur at all, whether quantum entanglement reveals something profound about the interconnected nature of the universe at its smallest scales, whether multiple realities or hidden variables influence outcomes in ways we cannot detect, or whether space and time themselves are not fundamental features of reality, but rather emerge from something more basic where separation itself is illusory. Decades of research have produced competing interpretations, from the Copenhagen interpretation to the many worlds hypothesis to pilot wave theory. Yet none fully resolves the conceptual paradox of how two systems that share no classical connection can exhibit perfect correlation when measured. And this ambiguity has become normalized within the scientific community in a way that allows researchers to use entanglement's mathematical formalism productively, while acknowledging that the underlying explanation remains genuinely open and contested among serious physicists. Perhaps most humbling is that this explanatory gap may reflect not a temporary limitation of human knowledge, but a fundamental boundary where our intuitions about causation, locality, and separability simply break down, suggesting that the question, "Why does entanglement happen?" might be as misguided as asking what exists north of the North Pole. Yet this acceptance of mystery is itself revealing. It suggests that the deepest scientific questions sometimes progress not by answering why, but by learning to ask better questions about what we mean by causation, measurement, and reality itself. At the heart of quantum mechanics lies one of the most perplexing and unsolved mysteries in all of science: a phenomenon that has troubled physicists for nearly a century and remains fundamentally mysterious despite our increasingly sophisticated understanding of the quantum realm. This phenomenon is known as wave function collapse, and it represents a paradox so profound that it challenges our basic assumptions about the nature of reality itself, observation, and the relationship between consciousness and the physical world. In quantum mechanics, particles exist in what physicists describe as a superposition, a simultaneous state of multiple possibilities, represented mathematically by something called a wave function that describes all the potential states a particle might occupy. When a physicist performs a measurement or observation of a quantum system, something extraordinary happens that defies classical intuition and continues to baffle even the most brilliant minds in theoretical physics. The wave function, which has been evolving smoothly and predictably according to the Schrödinger equation, suddenly and instantaneously collapses into a single, definite state, one of the possibilities that was previously superimposed with all the others. This collapse appears to occur instantaneously, faster than any physical process should reasonably allow, and it transforms probability into certainty in a way that seems to violate the continuity we observe in every other aspect of physics. The mysterious element lies in the mechanism itself, the actual process by which this collapse occurs, why it occurs precisely at the moment of observation, and what constitutes an observation in the first place, whether it requires conscious awareness or simply any physical interaction with the system. Different interpretations of quantum mechanics propose radically different answers to these questions, some suggesting that consciousness plays a fundamental role, others that the universe branches into parallel realities, and still others that the collapse is somehow illusory or that wave functions are merely tools for calculation rather than descriptions of objective reality. What makes this particularly troubling is that observation seems to change reality itself, suggesting that the act of measurement fundamentally alters the properties of what is being measured, creating an uncomfortable entanglement between observer and observed that contradicts our intuitive understanding of an objective reality existing independently of our awareness. Despite decades of experimental refinement and theoretical advancement, wave function collapse remains stubbornly mysterious, a fundamental feature of quantum mechanics that continues to resist complete explanation, suggesting that our deepest understanding of physical. At the most fundamental level of reality, something peculiar happens whenever we attempt to measure or observe a quantum system, and this phenomenon has puzzled physicists for nearly a century despite being one of the most carefully documented aspects of quantum mechanics. When a scientist sets up an experiment to determine the exact position of an electron, the act of measurement itself appears to force the electron into a definite state, collapsing what was previously a fuzzy cloud of probability into a single location. Yet the moment the observer stops looking, the electron seems to return to its wave-like, probabilistic state of existing in multiple places simultaneously. The mechanism underlying this effect remains deeply mysterious because it challenges our most basic intuitions about how observation should work, since logically we would expect that merely looking at something should reveal its pre-existing properties without fundamentally altering those properties in the process. The deeper puzzle emerges when we consider that quantum systems must be measured using photons or particles themselves, and these measuring particles inevitably interact with and disturb the system being observed, introducing uncertainty that cannot be separated from the act of measurement itself. Yet even accounting for this physical disturbance does not fully explain why the universe seems to behave so differently when we are watching versus when we are not. Some interpretations suggest that consciousness itself might play a role, that the act of awareness somehow collapses quantum possibilities into concrete reality, an idea that has captivated both physicists and philosophers despite remaining utterly unproven and resistant to rigorous testing. What persists as genuinely unsettling is that despite decades of experimental confirmation and mathematical formalism that works with extraordinary precision, we still cannot point to a single mechanism and say definitively that this is why observation affects quantum systems at such a fundamental level. The observer effect has become so normalized within physics that its profound strangeness has been somewhat obscured by technical language and mathematical abstraction. Yet when we step back and consider what it truly implies about the nature of reality, the mystery only deepens further into questions about whether observation creates reality or merely reveals it. Perhaps most troublingly, this ambiguity extends even to our most sophisticated experiments. We cannot design a test that definitively distinguishes between a universe where observation creates reality and one where it merely reveals pre-existing properties, leaving us with a profound epistemic barrier that may be fundamental to the structure of knowledge itself. For over a century, physicists have pursued one of humanity's most ambitious intellectual goals, a unified theory that explains all fundamental forces and particles in the universe through a single elegant framework. This quest, known as the search for a theory of everything, represents perhaps the most profound scientific mystery of our age, one that has consumed the careers of the greatest minds in physics and yet remains perpetually beyond our grasp. At the heart of this mystery lies a fundamental contradiction in our understanding of nature itself, for we possess two extraordinarily successful theories that describe the physical world with remarkable precision, yet these theories fundamentally cannot coexist within the same mathematical structure. General relativity, Einstein's revolutionary description of gravity, describes the large-scale structure of the universe, the curvature of spacetime, the orbits of planets, and the behavior of black holes with astonishing accuracy. Quantum mechanics, conversely, governs the realm of the infinitesimally small, describing atoms, electrons, photons, and the three other fundamental forces that shape the atomic and subatomic world with equal precision. Yet when physicists attempt to merge these two frameworks, when they try to apply quantum mechanics to gravity itself at the smallest scales, the mathematics collapses into infinities and contradictions, producing nonsensical results that suggest something is fundamentally wrong with our approach. Scientists have developed various candidate theories to resolve this crisis. String theory proposes that all particles are vibrating loops of energy in higher dimensions. Loop quantum gravity suggests spacetime itself is quantized into discrete loops. Supersymmetry predicts that every known particle has a yet undiscovered partner particle with different properties. Despite decades of research, billions in funding, and the collective genius of thousands of physicists worldwide, none of these approaches has achieved definitive experimental confirmation, and each remains shrouded in mathematical complexity so profound that only a handful of researchers truly understand their deepest implications. The persistence of this unsolved mystery, despite our technological advances and mathematical sophistication, reflects something profound about the limits of human knowledge and the extraordinary difficulty of glimpsing reality at its most fundamental level. Yet perhaps this very struggle itself offers valuable insight. The fact that nature resists our attempts at unification may suggest that reality operates according to principles far more subtle and interconnected than our current conceptual frameworks allow us to perceive, inviting us to expand not just our mathematics, but our fundamental intuition about how the U. Gravity remains one of the most profound mysteries in modern physics, existing in a peculiar state of incompleteness that has frustrated the world's greatest minds for nearly a century. While we have successfully married quantum mechanics with three of the four fundamental forces of nature, describing how electromagnetism, the strong nuclear force, and the weak nuclear force operate at the smallest scales of reality, gravity stubbornly refuses to be quantized in any consistent or elegant way. We can measure gravity's effects with exquisite precision, we can predict its behavior across cosmic distances with remarkable accuracy, and we can describe its fundamental nature through Einstein's general relativity as a curvature of spacetime itself. Yet the moment we attempt to apply the rules of quantum mechanics to gravity, our equations collapse into infinities and contradictions that our mathematical tools cannot resolve. At the heart of this mystery lies a conceptual tension that has proven remarkably resistant to resolution. General relativity describes gravity as a smooth, continuous warping of the fabric of spacetime caused by the presence of mass and energy, suggesting that gravity operates on all scales seamlessly, while quantum mechanics insists that all forces must be mediated by particles, discrete packages of energy that can be counted and quantified. When physicists have attempted to construct a quantum theory of gravity by introducing the graviton, a hypothetical particle that would carry gravitational force just as photons carry electromagnetic force, the mathematics generates predictions of infinite values in situations involving black holes, the Big Bang, and other extreme environments where gravity becomes extraordinarily strong. This suggests that something fundamental about our understanding is incomplete, that either quantum mechanics requires modification or general relativity breaks down at small scales, Or perhaps both theories need to be transcended by some deeper framework we have not yet discovered. The persistence of this problem, despite decades of intense effort from the brightest theoretical physicists on Earth, reveals something humbling about the nature of scientific progress. We have become comfortable with the notion that gravity remains fundamentally uncoupled from the quantum world, that it operates by different rules at different scales, that the universe apparently runs on two incompatible sets of instructions without the need for reconciliation at any accessible energy level. Yet this comfort masks a genuine incompleteness in our description of reality. The very moment we peer into the heart of a black hole or rewind time to the first fractions of a second after the Big Bang, this incompleteness becomes unavoidable, forcing us to confront the possibility. For decades, theoretical physicists have pursued one of the most ambitious goals in science: the development of string theory, a framework that attempts to unify all fundamental forces of nature into a single elegant mathematical structure where the smallest components of reality are not particles but vibrating strings of energy. Yet despite the intellectual investment of countless researchers and the mathematical sophistication of the theory itself, string theory remains unproven, existing in a peculiar state of scientific limbo where it generates almost no testable predictions that current or foreseeable technology could ever verify. The reason this matters so profoundly is that string theory requires the existence of extra dimensions beyond the three spatial dimensions and one temporal dimension we directly perceive. Dimensions that would need to be curled up so tightly at scales smaller than we can possibly measure that they remain forever beyond our experimental grasp. What makes this situation psychologically fascinating is how the scientific community has largely accepted this theoretical framework as intellectually respectable and worthy of pursuit, despite the fundamental violation of the principle that reproducible experimental evidence should form the foundation of scientific truth. The mechanism underlying this acceptance appears to be rooted in the sheer mathematical beauty of string theory and the genuine human desire to find the deepest underlying order of the universe, creating a situation where theoretical elegance becomes a substitute for empirical verification in ways that would be unthinkable in other scientific disciplines. Physicists and science communicators have normalized this departure from traditional scientific methodology by framing string theory as a necessary speculation about ultimate reality, one that might someday connect to observable phenomena even if current generations cannot possibly test it. The persistence of string theory research, despite the absence of proof, reveals something profound about how modern science operates at its theoretical frontiers, where the pursuit of conceptual unity sometimes supersedes the demands for measurable evidence, creating a domain where faith in mathematical structure functions almost like faith in religious doctrine. This paradox mirrors historical moments when scientific communities embraced theories ahead of experimental confirmation: the acceptance of invisible atoms before we could observe them, or the theoretical prediction of black holes long before their detection, suggesting that string theory's current status may represent either a necessary intermediate phase in scientific progress or a cautionary example of how the human mind can become entranced by mathematical elegance at the expense of empirical grounding. Our universe as we perceive it exists in three spatial dimensions plus time, a framework so fundamental to human experience that we rarely question its completeness. Yet theoretical physicists have long wondered whether additional spatial dimensions might exist beyond our ability to directly observe them, hidden from our everyday experience through mechanisms that keep them curled up or compressed at scales so infinitesimally small that our instruments cannot yet detect them. String theory, one of the leading candidates for a unified theory of physics that would reconcile quantum mechanics with general relativity, actually requires the existence of at least 10 spatial dimensions to function mathematically, suggesting that our familiar three-dimensional world might be merely a projection or limitation of a far richer geometric reality. And while this may sound like pure speculation born from theoretical necessity rather than experimental evidence, the mathematics works with an elegance that troubles and fascinates physicists in equal measure. The psychological appeal of extra dimensions lies partially in their ability to explain phenomena that seem paradoxical within our three-dimensional framework, offering a tantalizing possibility that mysteries of physics might dissolve once we properly account for these hidden geometries. Much as a two-dimensional being would struggle to understand how a three-dimensional sphere could penetrate their flat plane, appearing and disappearing seemingly at random. We have normalized this concept despite its profound strangeness because mathematics itself demands it, because the equations that describe reality at its smallest scales simply do not work without these extra dimensions, and because scientists have learned through centuries of discovery that the universe is far stranger than intuition suggests. So we accept what we cannot see because logic and mathematics point insistently toward its necessity. Yet the frustrating reality remains that despite decades of theoretical development and increasingly sophisticated experiments conducted at facilities like the Large Hadron Collider, we have found no direct experimental evidence that extra dimensions actually exist, no measurement that definitively confirms their presence, only the mathematical necessity that they should, which leaves us suspended between theoretical confidence and practical uncertainty. Peacefully accepting that the fabric of existence may be far more complex and hidden than we can currently perceive or measure. Perhaps most humbling is the possibility that future generations, armed with technologies we cannot yet imagine, might look back on our current three-dimensional perspective with the same gentle bewilderment we reserve for those who once believed the Earth was flat and thaw. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion so rapid and so profound that it fundamentally shaped everything we observe today. Yet the mechanism that initiated this cosmic inflation remains one of the deepest unsolved mysteries in theoretical physics and cosmology. We know that roughly 13.8 billion years ago, all of space, time, matter, and energy existed in an incomprehensibly dense state, and then somehow something triggered an inflationary epoch where the universe expanded faster than the speed of light could traverse it, smoothing out irregularities and setting the stage for the galaxies and stars we see in our night sky. Scientists have developed mathematical frameworks and elegant equations that describe how inflation would work once it begins. Yet the fundamental question of what actually caused it to start in the first place remains stubbornly elusive and resistant to our current understanding of physics. The leading theories propose various mechanisms such as quantum fluctuations in exotic scalar fields, phase transitions in the fabric of spacetime itself, or perhaps the decay of some primordial particle or field configuration. But none of these explanations has achieved consensus or been definitively confirmed through observational evidence. What makes this mystery particularly profound is that we cannot simply apply our intuitions about cause and effect, because the universe at that moment operated under physical laws that may have been entirely different from those governing reality today, and the very concepts of time and causality themselves might have functioned differently at the quantum scales involved. Physicists have become accustomed to this fundamental gap in our knowledge, integrating inflation into our standard cosmological models despite not truly understanding its origin, much in the way we might use a mathematical tool without fully comprehending its deeper significance. The persistence of this mystery highlights how even our most sophisticated theories contain hidden boundaries and unexamined assumptions, and it suggests that the true trigger for cosmic inflation may require entirely new physics or conceptual frameworks yet to be discovered. Perhaps the resolution will come from unexpected quarters, whether through revolutionary observations from next-generation telescopes peering into the cosmic microwave background's finest details, or from breakthroughs in quantum gravity that finally bridge the gap between the subatomic and the cosmic, reminding us that the universe's greatest secrets often yield only to those willing to question the very foundations of what we think we know. For centuries, humanity has gazed upward at the cosmos and wondered not merely about its origins, but about its inevitable end, a question that bridges physics, philosophy, and the deepest anxieties of the human condition itself. The mystery of the universe's ultimate fate remains one of science's most profound unsolved puzzles, one that challenges our understanding of time, energy, and existence itself. And despite tremendous advances in cosmology and observational astronomy, we still cannot definitively predict how everything will conclude. Contemporary physicists have identified several competing theories about what awaits the universe billions of years into the future, each supported by different observational evidence and mathematical frameworks, yet none universally accepted as certain truth. The Big Freeze scenario proposes that the universe will expand forever, gradually cooling as stars exhaust their fuel, and all matter spreads infinitely thin across an ever-enlarging void, creating a state of maximum entropy where no energy gradients exist to sustain any process or life. The Big Rip suggests something far more violent. If dark energy, that mysterious force driving cosmic acceleration, continues increasing in strength, it could eventually overcome all other forces and tear apart galaxies, stars, planets, atoms, and the very fabric of spacetime itself. The Big Crunch represents an older theory where gravity might eventually overcome expansion, causing the universe to collapse back upon itself in a mirror image of the Big Bang, compressing all matter and energy into a singularity. Heat death proposes a more subtle end, where although the universe persists, it reaches thermodynamic equilibrium, a state where no energy can be extracted or used, rendering all change impossible. What makes this mystery so resistant to resolution is that we cannot simply observe the universe's end directly, and our predictions depend heavily upon understanding dark energy, a substance comprising roughly 70% of all energy in the universe, yet remaining almost entirely mysterious in terms of its fundamental nature and behavior. We have normalized our profound ignorance about cosmic destiny by compartmentalizing it, discussing these scenarios in academic terms while barely acknowledging that none of them offer any hope for permanent survival or escape. Yet this acceptance allows science to continue investigating what clues the universe itself might reveal about its own conclusion. Perhaps the most humbling aspect of this inquiry is that the universe's fate may ultimately be indifferent to our understanding of it. Whether we solve this mystery or not, the cosmos will follow its predetermined trajectory, indifferent to our theories and our anxieties about endings. Deep within the cosmos, galaxies across an enormous region of space appear to be moving in a coordinated direction, all being pulled toward an unseen gravitational force that astronomers have named the Great Attractor, a phenomenon that challenges our understanding of the universe's structure and composition. When scientists mapped the movements of thousands of galaxies across millions of light years, they discovered that these vast island universes, some containing billions of stars, were not randomly distributed or moving in random directions as one might expect, but instead seemed to be flowing together toward a region of space located approximately 250 million light-years away in the direction of the Norma cluster, as if drawn by an invisible cosmic hand. The mystery deepens because when astronomers pointed their most powerful telescopes toward this region of space, they found that the visible matter they could observe, the stars, galaxies, and nebulae, did not contain anywhere near enough mass to create such powerful gravitational pull, yet the galaxies continued their inexorable motion toward this location, as if responding to something vast and hidden from view. The mechanism behind our persistent puzzlement involves the fundamental disconnect between what we can observe and what we must logically exist, for gravity requires mass, and yet the Great Attractor appears to exert far more gravitational influence than all the visible matter in that region could possibly produce, leading scientists to theorize about dark matter, unknown cosmic structures. Or perhaps the influence of even more distant massive objects whose gravity reaches across unimaginable distances. Our minds struggle to reconcile this observation with our models of how the universe should behave, creating a profound tension between what we measure and what we can explain, and this cognitive dissonance has driven decades of research without producing a definitive answer that satisfies all observations and theories. What makes this mystery particularly persistent despite our technological advancement is how we have integrated it into our understanding while simultaneously avoiding the uncomfortable implications it carries. For the Great Attractor reminds us that the universe contains vast regions we cannot see, forces we cannot measure directly, and structures potentially far larger than anything we have thus far conceived. And yet we continue our work as if this gap in knowledge is merely a temporary problem awaiting better instruments rather than a fundamental limitation that may be far more profound. Perhaps the Great Attractor ultimately represents not merely an unsolved problem, but rather evidence that our maps of reality remain fundamentally incomplete, with vast territories of the cosmos still bare. Deep within the vast cosmic web, astronomers have detected something that should not exist according to our current understanding of the universe, a peculiar motion that seems to pull entire galaxy clusters toward an unknown region of space in a direction that defies explanation. This phenomenon, known as dark flow, was first identified in 2008 when researchers analyzing the motion of galaxy clusters across billions of light-years noticed a persistent directional bias that could not be accounted for by the known distribution of matter in the universe. The clusters appeared to be streaming together toward a point located beyond the observable edge of our cosmic horizon, suggesting the gravitational influence of something so massive and so distant that we cannot see it with any of our telescopes or instruments. The mechanism behind this observation involves the subtle motion of galaxy clusters as they drift through space, and when scientists examined these movements with unprecedented precision using data from various astronomical surveys, they found that these clusters were not moving randomly, but rather shared a coherent velocity component pointing toward a particular direction in space. This collective motion implies the presence of an enormous gravitational attractor, something researchers initially speculated might be a colossal concentration of dark matter or perhaps even an entire universe-sized structure lying beyond what we can observe. The most fascinating aspect of dark flow is how it persists as a genuine scientific puzzle despite decades of subsequent analysis and refinement, because alternative explanations have been proposed and tested, including the possibility that dark flow might be an artifact of measurement errors, statistical anomalies in the data, or perhaps related to the way we measure the cosmic microwave background radiation. Some researchers suggest that what we interpret as dark flow could simply be the result of how we define our reference frame, the fundamental coordinate system against which we measure all cosmic motion. Yet even with these alternative theories, the phenomenon continues to challenge our comprehension of the universe's large-scale structure and our place within it, representing a reminder that despite our sophisticated instruments and mathematical models, the cosmos still harbors secrets that lie just beyond our ability to fully perceive or understand. Should dark flow ultimately prove to be a genuine cosmological phenomenon rather than an observational artifact, it would fundamentally reshape our understanding of the universe's structure and composition, possibly indicating the existence of massive structures or even other universes beyond our cosmic horizon. When astronomers first began measuring the rotational speeds of distant galaxies in the mid-20th century, they encountered a puzzling discrepancy that would fundamentally challenge our understanding of the cosmos. According to the laws of physics as we understood them, galaxies should rotate like cosmic wheels, with stars closer to the galactic center moving faster than those at the outer edges, much as planets orbit more quickly when closer to the sun. However, observations revealed something entirely different. Stars at the outer edges of galaxies were moving far too quickly relative to what the visible matter present could possibly account for. The gravitational pull generated by all the stars, gas, and dust we could actually see was insufficient to hold these outer stars in their observed orbits at their observed velocities. By all logical calculations, these stars should have been flung outward into space like passengers thrown from a spinning carnival ride, yet they remained mysteriously bound to their galaxies. This observation emerged repeatedly across galaxy after galaxy, suggesting not an isolated anomaly, but rather a systematic gap in our fundamental knowledge. The mechanism underlying this puzzle involves a straightforward application of Newton's laws of motion and gravitational theory. When we measure how quickly a galaxy rotates, we can calculate the total mass that must be present to maintain those orbital velocities. The mathematics is elegant and reliable, tested across centuries of astronomical observation. Yet when we add up all the observable mass, we consistently find ourselves short by a factor of 5 to 10 times or more. This is not a minor discrepancy, but a gaping chasm suggesting that the universe contains far more matter than we can directly observe through light and radiation. The response to this mystery has been the hypothesis of dark matter, an invisible substance proposed to fill this gravitational gap, yet dark matter itself remains undetected and theoretical. What is remarkable about how we have normalized this situation is how readily the scientific community accepted the existence of an entire category of matter 5 times more abundant than all the ordinary matter comprising stars and planets, without ever definitively proving it exists. We have built an elaborate theoretical framework around the presumed nature and properties of dark matter. We map its expected distribution throughout the universe, and we design experiments to detect it, yet fundamentally we are building an edifice upon a mystery rather than a solved problem. The galaxy rotation problem persists as a humbling reminder that our observations reveal only a portion of reality. Deep within the mathematical frameworks of particle physics exists a possibility so profound and terrifying in its implications that physicists have spent decades attempting to either prove it impossible or calculate the odds of its occurrence. And this possibility is known as vacuum decay, a theoretical event in which the quantum vacuum that permeates all of existence could spontaneously transition from its current state to a lower energy state, and in doing so, would unleash a catastrophic expansion of destruction across the entire universe at the speed of light. The concept emerges from quantum field theory, which describes reality not as a collection of solid particles, but rather as fields that vibrate and fluctuate at quantum scales, and these fields exist in what physicists call a vacuum state, the lowest energy configuration theoretically possible, yet according to the mathematics, this vacuum state might not actually be the lowest energy state after all, but rather a metastable state. Like a ball balanced precariously atop a hill rather than resting in a valley. If this is true, then the vacuum could theoretically collapse into a lower energy state through quantum tunneling, an event that would create a bubble of true vacuum that would expand outward in all directions at light speed, and everything within that bubble, including atoms, stars, galaxies, and all fundamental physics as we understand it, would be instantly transformed into something utterly different and incomprehensible. The mechanism that allows physicists to contemplate this scenario lies in our measurements of the Higgs boson and the top quark, particles whose masses and interaction strengths, when calculated through quantum field equations, seem to suggest that our vacuum might indeed be unstable, existing in a false minimum from which it could theoretically fall. And the only question becomes whether the probability of this event occurring is infinitesimally small or merely improbable. What makes this threat particularly unsettling is that we have normalized it as simply another theoretical possibility in physics, something to be calculated and debated in academic papers rather than treated as an existential emergency, even though if true, it would represent the most absolute extinction event imaginable, one that would erase not just humanity or Earth or our galaxy, but the very foundation of physical reality itself. And yet scientists continue their work without visible anxiety or urgency, perhaps because the calculations suggest the probability is so vanishingly small that we may have billions or trillions of years before such an event might occur, if it occurs at all. Deep within the structure of the universe, scattered across billions of light years, exist regions of almost incomprehensible emptiness known as cosmic voids, vast expanses where galaxies are nearly absent and the density of matter plummets to levels far below the cosmic average. These voids can stretch for hundreds of millions of light years, creating enormous bubbles within the fabric of spacetime itself. And while astronomers have mapped their locations and measured their dimensions with increasing precision over recent decades, the fundamental mechanisms driving their formation and evolution remain profoundly mysterious and poorly understood. The prevailing theoretical framework suggests that in the earliest moments following the Big Bang, quantum fluctuations in the primordial universe were stretched to cosmic scales by inflation, creating regions of slightly higher and slightly lower density. Yet the question of how these minuscule initial variations grew into such colossal structures defies complete explanation, as the standard models of structure formation struggle to reproduce the observed properties of voids with full fidelity. One might expect that voids simply represent regions where matter was randomly distributed in lower concentrations, areas where gravity had less material to work with and therefore less capacity to pull things together. Yet this explanation encounters significant complications when examined rigorously, for the dynamics of void expansion and the mechanisms maintaining their vast emptiness suggest processes more complex than passive underdensities. The curious persistence of cosmic voids, despite the universe's general tendency toward gravitational collapse, introduces a puzzle that keeps theoretical cosmologists engaged in heated debates. As the voids appear to expand along with the cosmic expansion itself, their emptiness seemingly reinforced rather than diminished by the passage of time. We have normalized this cosmic mystery by incorporating voids into our standard models without fully grasping the mechanisms that created them. Accepting their existence as a natural consequence of early universe physics, even as fundamental questions about their formation, stability, and role in cosmic evolution remain tantalizingly unanswered and continue to challenge our deepest understanding of how the universe organized itself into its current magnificent and bewildering structure. Recent observations from surveys like the Sloan Digital Sky Survey have revealed voids with dimensions exceeding 300 million light-years, forcing us to confront whether our understanding of gravity, dark matter distribution, and cosmic expansion itself, may require fundamental revision to account for such staggering scales of emptiness. Between the orbits of Mars and Jupiter, traveling through the vast emptiness of space at tremendous velocities, two spacecraft named Pioneer 10 and Pioneer 11 have been drifting through the solar system since the 1970s, carrying with them a mystery that has puzzled physicists and astronomers for decades. These unmanned probes were launched during humanity's earliest ambitious attempts to explore the outer planets, and as they journeyed deeper into the cosmos, scientists on Earth monitored their trajectories with extraordinary precision, measuring their positions and velocities through careful radio signal analysis. What they discovered was profoundly strange and unexplained. Both Pioneer spacecraft were experiencing a slight but consistent deceleration, a gentle push pulling them back toward the sun with a force that classical physics could not adequately account for or explain. The acceleration was extraordinarily small, measuring only about 1/1000th of Earth's gravitational pull, yet it was persistent and undeniable, appearing in the spacecraft's radio Doppler data like a whisper of mystery written across the cosmic void. Scientists proposed numerous explanations for this enigmatic phenomenon, examining everything from unaccounted solar radiation pressure to asymmetric heat emissions from the spacecraft's radioisotope thermoelectric generators. Yet none of these conventional theories could completely explain what was being observed. The Pioneer anomaly persisted as one of astronomy's most intriguing puzzles for decades, captured in careful measurements and mathematical models that could not be fully reconciled with established physical laws. The mystery eventually faded from prominent scientific attention as new spacecraft and improved measurement techniques became available, and the pioneers themselves gradually fell silent as their power sources depleted, leaving their anomaly partially unresolved in the historical record of space exploration. Yet in retrospect, the Pioneer anomaly served as a humbling reminder that even in an age of advanced technology and sophisticated understanding, the universe still harbors secrets waiting in the spaces between the stars, challenges to our knowledge that demand continued investigation and intellectual humility from those who seek to comprehend the cosmos. Some researchers have since revisited the Pioneer data with modern computational methods, suggesting that much of the anomaly might be attributable to thermal recoil forces previously underestimated, though debate continues among specialists about whether all aspects of the mystery have truly been resolved. This legacy reminds us that scientific understanding is not static, but evolves through persistent questioning and re-examination of puzzling observations. Every single day, millions of people around the world undergo surgical procedures where they are rendered completely unconscious by chemical compounds administered through injection or inhalation. Yet despite over a century and a half of widespread use, the fundamental mechanism by which anesthesia actually works remains one of modern medicine's most profound unsolved mysteries. We know empirically that certain molecules, ranging from simple gases like nitrous oxide to complex organic compounds like propofol and sevoflurane, reliably produce a state of unconsciousness, muscle relaxation, and inability to feel pain. Yet the precise way these chemically diverse substances interact with the brain to produce such consistent results has eluded complete scientific understanding. Anesthetics work on the central nervous system, this much we have established, and we have identified various receptor sites and neural pathways that seem to be involved in their action, including effects on gamma-aminobutyric acid receptors, N-methyl D-aspartate receptors, and potassium channels. Yet no single unified theory successfully explains how drugs with vastly different molecular structures and properties all manage to switch off consciousness with such remarkable reliability. The mystery deepens when we consider that anesthetics seem to work through multiple simultaneous mechanisms, and that different anesthetic agents may achieve unconsciousness through somewhat different pathways, suggesting that consciousness itself might not be dependent on any single neurochemical process, but rather on some emergent property of neural activity that we have yet to fully comprehend. We have developed increasingly sophisticated theories about how anesthetics might suppress integrated information processing in the brain or disrupt the communication between different neural networks necessary for conscious awareness. Yet we cannot fully predict which new chemical compounds will be effective anesthetics or why some work better than others. And we still struggle to understand why we need multiple drugs during surgery rather than a single agent that could accomplish all the necessary effects. What is perhaps most remarkable is how we have normalized this profound ignorance, performing millions of surgeries each year with anesthetics whose fundamental mechanisms remain mysterious, trusting in statistical safety records and empirical protocols while continuing to refine our understanding in incremental ways, accepting that we can reliably render people unconscious without fully knowing why, which perhaps represents one of medicine's strangest achievements. The successful application of a process we do not truly understand. Imagine yourself sitting in a quiet meeting, completely alert and focused, when suddenly someone across the table opens their mouth wide in a deep yawn, and within moments you feel an irresistible urge to do the same, your own jaw stretching involuntarily as if connected by invisible strings to theirs. This phenomenon, known as contagious yawning, is one of the most perplexing and widespread neurological responses that humans experience, affecting approximately 60 to 80% of the population to varying degrees, and it happens with remarkable consistency across cultures and age groups around the world. The experience itself is undeniable and immediate. We see or hear someone yawn, and our brains seem to hijack our muscles, compelling us to mirror that same action, even when we were moments before perfectly comfortable and alert. Scientists have struggled for decades to explain why our nervous systems would evolve such an apparently pointless mechanism, why we would be neurologically wired to automatically replicate a behavior that serves no obvious survival function or social benefit. The leading theories suggest connections to empathy and mirror neuron systems, the idea being that our brains are inherently designed to simulate and understand the actions and intentions of others, and yawning might simply be a byproduct of this deeper mimicry instinct that once served important purposes in social bonding and group synchronization among our ancestors. Yet the mystery deepens when we consider that this response seems to operate largely outside our conscious control, that we cannot simply decide not to yawn when triggered, and that even seeing a photograph of someone yawning or merely reading the word yawn written on a page can activate this unconscious motor response. What makes yawning contagion truly enigmatic is that it persists as a fundamental aspect of human neurology despite the complete absence of any clear reason why it should, and we have simply accepted it as normal, as something that everyone experiences, when in fact it represents a strange vulnerability in our neural architecture, a moment where the boundaries between self and other blur in ways we still cannot fully comprehend or explain. Perhaps most intriguingly, contagious yawning appears to develop later in childhood and strengthens throughout life, suggesting that this neural susceptibility is not fixed, but rather grows as our brains become more sophisticated at reading and resonating with the internal states of those around us, making it less a primitive reflex and more a marker of our deepening capacity for social understanding. Consider the peculiar sound that emerges from human beings when something strikes them as amusing, a rhythmic vocalization that convulses the body and produces tears from the eyes, and you encounter one of the most enigmatic behaviors in our species' behavioral repertoire. Laughter appears across all human cultures in remarkably similar forms, yet its evolutionary origins remain shrouded in mystery and competing theories that have yet to reach consensus among researchers. The physical act of laughter involves the simultaneous activation of multiple muscle groups, the diaphragm contracting in rapid succession, the face contorting into what we recognize as a smile, and the vocal cords vibrating to produce sound. Yet this complex choreography seems to serve no obvious biological purpose in the way that fear or pain serves a clear protective function. When we examine laughter across our primate relatives, we find that chimpanzees and other apes produce vocalizations during play that bear a superficial resemblance to human laughter, leading some researchers to propose that laughter evolved from social bonding, behaviors that strengthened group cohesion during moments of reduced tension and increased safety. The theory suggests that early humans who could laugh together during play and non-threatening social interactions formed stronger interpersonal bonds, and those strengthened bonds may have conferred survival advantages through improved cooperation and group stability, though the precise mechanisms by which this translation from individual behavior to evolutionary advantage might have occurred remain remarkably unclear. Yet what persists as genuinely puzzling is that laughter today has become something far more complex than a simple social bonding mechanism, transformed through cultural evolution into an intricate signaling system that communicates not just genuine amusement, but also sarcasm, nervousness, discomfort, and even complete falsehood. We laugh when we are uncomfortable in social situations where silence would feel awkward. We produce laughter that is performative and strategic rather than spontaneous. We laugh in ways that are calibrated to impress others or to navigate social hierarchies. And these uses of laughter seem divorced entirely from any ancestral function related to group bonding or play. The mystery deepens when we acknowledge that we are fully aware that much of our laughter is manufactured, and yet we continue the practice without apparent cost to our social relationships, suggesting that the social contract itself has evolved to accept and even expect a degree of performative laughter that bears little resemblance to authentic responses to humor. Approximately 10% of the human population is left-handed, a proportion that has remained relatively consistent across cultures and throughout recorded history, despite centuries of active suppression and social pressure designed to eliminate the trait entirely. Throughout much of the 20th century, left-handed children in schools across North America and Europe were forcibly retrained to write with their right hands, subjected to physical punishment, ridicule, and shame in the pursuit of conformity to a right-handed standard. Teachers would tie children's left hands behind their backs, strike their knuckles with rulers, and create elaborate systems of punishment for any deviation from right-handed writing. Yet despite these intensive and often traumatic interventions, left-handedness has persisted at roughly the same rate across generations. The biological basis for this persistence appears rooted in the fundamental asymmetry of the human brain, where the left hemisphere typically controls the right side of the body and processes sequential, analytical information, while the right hemisphere governs the left side and handles spatial and intuitive reasoning. The precise genetic mechanisms that determine handedness remain incompletely understood, though research suggests it involves multiple genes rather than a single inherited factor, making it far more complex to simply breed out of a population than early 20th century behaviorists believed possible. What makes this phenomenon particularly intriguing from a scientific perspective is that left-handedness offers no apparent evolutionary disadvantage in the modern world and arguably presents certain cognitive advantages in specific domains such as creative thinking and spatial reasoning. Yet the trait continues to be perceived as unusual or requiring correction by many societies. Despite modern acceptance and the recognition that forcing handedness change causes psychological harm and learning difficulties, left-handed individuals still encounter a world designed entirely for right-handed use, from school desks to computer mice to can openers and scissors. The persistence of left-handedness, despite both historical suppression and present-day environmental inconvenience, suggests that whatever neurological and genetic factors determine handedness are robust and resistant to modification, representing one of the many ways human biology maintains diversity even when social structures actively work to eliminate it. This resilience mirrors other biological traits that societies have attempted to suppress, from red hair to certain eye colors, suggesting that human diversity is fundamentally constrained not by social preference, but by the underlying architecture of our genetics and neurobiology, which maintains variation regardless. One of the most enduring questions in modern biology concerns the genetic basis of sexual orientation, a mystery that has captivated researchers for decades as they attempt to understand whether homosexuality is determined by our DNA, shaped by environmental factors, or influenced by some complex interplay between nature and nurture that we have yet to fully comprehend. Scientists have conducted numerous twin studies, examined chromosomal patterns, and analyzed genetic markers in hopes of identifying a definitive biological explanation for sexual orientation. Yet the results have remained frustratingly inconclusive and often contradictory, suggesting that if genetics does play a role, it operates through mechanisms far more intricate than initially theorized. Multiple genome-wide association studies have identified certain genetic variants that correlate with same-sex attraction, but these variants account for only a small percentage of the variation observed in human populations, and no single gene or even cluster of genes has emerged as the primary determinant of sexual orientation. The psychological mechanism underlying this scientific pursuit reflects our deep human desire to categorize and explain fundamental aspects of identity through reductionist biological frameworks, as if reducing complex human experience to genetic sequences might grant us a sense of understanding and predictability about characteristics that have always seemed mysterious and difficult to measure objectively. We tend to assume that if we can locate a genetic cause for something, we can better understand it, control it, or perhaps modify it, and this assumption has driven considerable research funding and theoretical development in the field of behavioral genetics. What makes this mystery particularly persistent is the fundamental problem of measurement itself. For sexual orientation exists on a spectrum, varies across cultures and historical periods, and involves psychological, emotional, and behavioral components that resist simple quantification or binary classification. Despite decades of investigation using increasingly sophisticated molecular techniques, researchers have largely come to accept that sexual orientation likely emerges from multiple interacting genetic factors combined with prenatal hormonal influences, early childhood experiences, and countless other variables that create unique developmental pathways in each individual. The scientific community has gradually normalized the uncertainty surrounding this question, recognizing that not all biological phenomena can be neatly explained through genetic determinism alone, and that the very framework of seeking a genetic origin for sexual orientation may itself be based on cultural assumptions rather than biological reality. Despite centuries of medical advancement and billions of dollars invested in longevity research, humanity still lacks a fundamental understanding of why aging occurs at all, and this mystery persists as one of science's most pressing unsolved puzzles. We observe aging happening all around us every single day. Our skin wrinkles, our joints stiffen, our hair grays, our organs gradually lose their efficiency, and eventually our bodies fail us completely. Yet we cannot definitively explain the underlying biological mechanism that causes this universal phenomenon. Scientists have proposed numerous theories about aging, ranging from the accumulation of cellular damage over time to telomere shortening, mitochondrial dysfunction, senescent cell accumulation, and epigenetic changes. But none of these explanations fully account for why living organisms age the way they do, or why the aging process is fundamentally inescapable across virtually all species. The human body replaces most of its cells regularly throughout life, yet somehow the overall system still deteriorates, suggesting that aging is not simply about individual cells wearing out, but rather involves some deeper systemic decline that we do not yet comprehend. The psychological mechanism that keeps us accepting aging as inevitable stems from the simple fact that we have always observed it, making it feel like a natural law rather than a problem that might someday be solved. And this normalization of aging in human consciousness causes us to invest relatively little research effort into understanding it compared to how much we spend fighting individual diseases. We treat the symptoms of aging, wrinkles, bone loss, cognitive decline, as separate medical problems rather than manifestations of a single underlying process, which fragments our research efforts and prevents the kind of unified approach that might reveal aging's true root cause. What makes this mystery particularly profound is that aging appears to serve no evolutionary purpose, yet it persists universally, suggesting either that we have fundamentally misunderstood how evolution shapes aging, or that aging is an inevitable byproduct of being a complex biological system. And until we solve this core mystery, all our efforts to extend human lifespan remain somewhat like treating symptoms while ignoring the disease itself. The sobering reality is that even our most promising interventions, from caloric restriction to senolytics to genetic therapies, have only marginally extended lifespan in laboratory organisms, suggesting we remain fundamentally limited by our incomplete understanding of what aging actually is at its most basic level. For as long as humans have kept records, our species has demonstrated a curious biological ceiling, a maximum age beyond which the human body seems remarkably reluctant to venture, and this phenomenon remains one of the most profound unsolved mysteries in gerontology and cellular biology. The oldest verified person to have ever lived was Jeanne Calment of France, who reached the age of 122 years and 164 days, and since her death in 1997, no human has come close to surpassing this record, despite dramatic improvements in medicine, nutrition, healthcare access, and living conditions across the developed world. This suggests that there exists some fundamental biological constraint, some invisible wall encoded within our very cells, that prevents us from extending our lives beyond a certain threshold regardless of external circumstances. Scientists have discovered that our cells contain telomeres, protective caps on our chromosomes that shorten with each division, and once these telomeres reach a critical length, cells enter senescence or die entirely, which appears to be a primary mechanism limiting our lifespan, yet understanding exactly how and why this system operates as it does remains largely mysterious. The Hayflick limit demonstrates that normal human cells can only divide between 50 and 70 times in laboratory conditions before they stop dividing altogether, suggesting that aging is not merely the accumulation of random damage, but rather a programmed biological process, though whether this programming serves some evolutionary purpose or represents a vestigial remnant of ancient survival mechanisms remains unclear. What makes this mystery particularly compelling is that some organisms, such as certain jellyfish and some planarian worms, appear to possess biological immortality or negligible senescence, aging so slowly that they might theoretically live indefinitely, yet humans and most large mammals follow a strict timeline that seems immovable. We have normalized the idea that human life must end around a century, accepting it as inevitable and natural. Yet the persistence of this maximum lifespan across populations and centuries, despite the revolutionary changes in how we live, suggests that we are constrained by something deeper than mere accumulation of environmental damage, something written into our molecular code that we have yet to fully decipher. Perhaps the most unsettling implication is that even if we solve aging itself, eliminating disease, halting cellular damage, and reversing accumulated wear, we might still find ourselves pressed against this biological ceiling, suggesting that the maximum lifespan limit represents not a problem to be solved, but a fundamental property of human existence that we must learn to. Despite centuries of medical advancement and billions of dollars invested in research, cancer remains one of humanity's most elusive adversaries, and yet the dream of discovering a singular ultimate cure persists in the collective imagination with remarkable tenacity. The reality of cancer itself is far more complex than popular culture often suggests, for cancer is not one disease but rather hundreds of distinct diseases, each with its own genetic mutations, biological behaviors, cellular origins, and resistance mechanisms, meaning that a treatment effective against one type of leukemia might prove entirely useless against pancreatic cancer or melanoma. Yet the narrative of the ultimate cure, a single breakthrough, a miraculous pill, a revolutionary therapy that will eliminate cancer once and for all, continues to capture headlines, inspire donations, and fuel hope in ways that the messy, incremental reality of modern oncology simply cannot match. The psychological mechanism underlying this persistent belief likely stems from humanity's profound need to frame complex, terrifying problems in terms of simple solutions. For the idea of one cure is far more comforting and comprehensible than accepting that cancer treatment will forever be an evolving battle requiring constant innovation, personalization, and adaptation. We have normalized this vision through decades of media representation, celebrity testimonials about miraculous recoveries, and the very real successes of immunotherapy and targeted medicine, which do indeed represent extraordinary progress, but are misinterpreted as steps toward a singular ultimate solution rather than components of an increasingly sophisticated arsenal. The persistence of this mythology reveals something profound about human psychology, our tendency to seek closure and finality in domains where uncertainty is the only honest answer, and our difficulty in accepting that some of humanity's greatest enemies might never be defeated definitively, but only managed with ever greater skill and compassion. Perhaps this acceptance itself, that cancer will remain a lifelong challenge rather than a vanquished foe, represents a more mature and ultimately more empowering form of hope, one that redirects our energy from waiting for miracles toward building healthcare systems capable of early detection, personalized treatment, and compassionate care for the millions living with cancer as a chronic condition. In countries where such systems have been implemented, where screening is universal, treatment is tailored to individual tumor genetics, and supportive care is robust, survival rates have climbed steadily, demonstrating that the real victory against cancer lies not in discovering one magical cure, but in the unglamorous work of prevention, early intervention, and the relentless. Prion diseases represent one of the most peculiar and devastating categories of neurodegenerative disorders known to modern medicine, and despite decades of intensive research, we still lack a reliable cure or even a truly effective treatment protocol that can halt their progression. These diseases, which include conditions such as Creutzfeldt-Jakob disease in humans, scrapie in sheep, and chronic wasting disease in deer and elk, are caused by misfolded proteins called prions that somehow induce normal proteins in the brain to adopt the same aberrant shape, creating a chain reaction of misfolding that cascades through neural tissue like dominoes falling in slow motion. The tragedy of prion diseases lies in their absolute lethality once symptoms emerge, yet the mystery deepens when we consider that scientists have known the basic mechanism for decades, understanding that a single misfolded protein can theoretically trigger this catastrophic transformation, and yet they remain unable to translate this knowledge into any meaningful therapeutic intervention. The psychological mechanism behind our struggle with prion diseases stems partly from their fundamental challenge to our understanding of infection itself. As they require no genetic material whatsoever, no DNA or RNA, operating instead through a mechanism so alien to conventional microbiology that for years the very concept was rejected by the scientific establishment as theoretically impossible. We have normalized this helplessness by compartmentalizing prion diseases as rare curiosities, affecting perhaps only thousands annually worldwide, which allows us to view them as peripheral concerns rather than urgent priorities demanding revolutionary approaches to protein folding and neurodegeneration. The persistence of this unsolved problem reflects a deeper reality about the limits of conventional pharmaceutical development. For prion diseases cannot be treated like most other diseases because their pathology represents a fundamental corruption of the protein folding machinery itself, making traditional drug targets elusive and conventional antibiotics or antivirals utterly useless. Leaving researchers grasping for entirely novel therapeutic strategies that might somehow intercede in the protein misfolding cascade before irreversible neural destruction occurs. Yet such strategies remain largely theoretical and untested in human populations. Recent experimental approaches, including immunotherapy targeting misfolded prions, small molecules designed to stabilize normal protein conformations, and even gene therapy strategies, offer genuine promise, yet each faces the formidable obstacle of crossing the blood-brain barrier and reaching sufficient concentrations within neural tissue before irreversible damage accumulates, a temporal constraint T. For over a century, researchers have pursued the underlying cause of Alzheimer's disease with remarkable intensity, yet the fundamental mystery remains largely unsolved, presenting one of modern medicine's most perplexing paradoxes. The disease itself manifests through progressive cognitive decline, memory loss, and eventual complete deterioration of mental function, affecting millions of individuals worldwide, yet despite countless billions invested in research and decades of intensive study, we still cannot definitively explain what triggers this devastating neurological condition in the first place. The prevailing hypothesis suggests that accumulation of amyloid beta proteins and tau tangles in the brain causes neuronal death and cognitive decline, a theory so widely accepted that it has dominated research agendas and pharmaceutical development for generations, leading companies to invest enormous resources into drugs designed to target and eliminate these protein formations. However, the logic underlying this assumption begins to fracture upon close examination, because many individuals possess significant amyloid and tau buildup in their brains, yet never develop symptoms, while conversely, some patients exhibit severe Alzheimer's symptoms with minimal protein accumulation, suggesting that these hallmark proteins might be consequences rather than causes, or perhaps merely correlates of a deeper underlying process we have yet to identify. The scientific community has become so invested in this amyloid hypothesis that alternative explanations have received comparatively minimal funding and attention, including theories involving chronic inflammation, vascular dysfunction, viral infections, mitochondrial dysfunction, or complex interactions between multiple factors that might vary significantly between individuals. This represents a peculiar state of normalized uncertainty, where we have constructed an elaborate framework of understanding around mechanisms we have not truly proven, where pharmaceutical interventions based on removing amyloid proteins have largely failed to slow cognitive decline in meaningful ways. Yet the hypothesis persists as the dominant paradigm, driving research directions and clinical trial designs as if the mechanism were already established. The true cause of Alzheimer's disease remains hidden beneath layers of assumptions and incomplete data, waiting perhaps for a fundamentally different approach to reveal what we have been overlooking all along. Perhaps that different approach will require us to shift our focus from looking exclusively at what accumulates in the brain to examining why the brain's natural clearing mechanisms, its glymphatic system, immune function, and cellular waste disposal processes, may be failing in the first place, recognizing that the human body possesses one of nature's most sophisticated defense systems, a complex network of cells and molecules designed to recognize and eliminate threats like bacteria, viruses, and parasites. Yet sometimes this protective mechanism turns inward and begins attacking the very tissues it evolved to protect, resulting in what scientists call autoimmune disease, a category of conditions that includes rheumatoid arthritis, lupus, celiac disease, type 1 diabetes, and dozens of others, collectively affecting millions of people worldwide. What remains profoundly mysterious is not the existence of autoimmune conditions themselves, but rather the precise triggers that cause the immune system to fundamentally misidentify the body's own cells as foreign invaders requiring destruction. A question that has puzzled immunologists and researchers for decades despite enormous advances in our understanding of cellular biology and genetic expression. The leading theories suggest that autoimmune diseases arise from a combination of genetic predisposition and environmental factors, meaning that certain individuals inherit genes that make their immune systems vulnerable to confusion, and then some specific environmental event or exposure acts as the spark that ignites the misdirected immune response. Yet identifying these exact environmental triggers has proven remarkably elusive because they vary greatly between individuals and even between different presentations of the same disease. Researchers have proposed candidates, including viral infections that structurally resemble proteins in human tissue, thereby confusing immune cells through a process called molecular mimicry, dietary components that might interact with intestinal barriers in ways that breach immune tolerance, stress hormones that alter immune regulation at critical developmental windows, and exposure to ultraviolet radiation or certain medications that trigger dormant genetic vulnerabilities. Yet no single trigger has been definitively proven across all cases or even consistently within a single disease category. The persistence of this mystery reflects a deeper complexity in immunology itself, for the boundary between a healthy immune system and an autoimmune one appears less like a clear threshold and more like a subtle spectrum where multiple small factors accumulate until the system tips into self-directed destruction, making it extraordinarily difficult to identify which specific moments or exposures constitute the actual turning point in any individual's disease development. This accumulation model suggests that prevention and early intervention may require identifying not single smoking guns, but rather patterns of vulnerability, which is why current research increasingly focuses on tracking immune system changes across populations. For decades, scientists studying the human genome made a curious discovery that challenged fundamental assumptions about how life works, as they found that approximately 98% of our DNA does not code for proteins, meaning it does not provide instructions for building the amino acids that form the structures and functions of our bodies, and this vast majority of genetic material was initially dismissed and labeled as junk DNA. A seemingly useless remnant of evolutionary history that served no apparent purpose and accumulated over millions of years without consequence. The reasoning behind this classification seemed straightforward at the time, since researchers operated under the central dogma that DNA's primary function was protein coding, and therefore any sequence that did not participate in this process must be superfluous genetic junk that natural selection had not bothered to eliminate, perhaps because it caused no harm and consumed negligible cellular resources. However, as molecular biology techniques advanced dramatically throughout the 1990s and 2000s, scientists began discovering that this junk DNA actually performs numerous critical functions that regulate gene expression, control when and where proteins are produced, provide structural organization for chromosomes, and even produce regulatory RNA molecules that fine-tune biological processes in extraordinarily sophisticated ways. Yet the term junk DNA persisted in scientific literature and popular consciousness despite mounting evidence of its functional importance. The persistence of this misnomer reveals something profound about how scientific understanding accumulates and normalizes, as the initial categorization became embedded in textbooks, research frameworks, and the collective memory of the scientific community, making it psychologically and institutionally difficult to completely overturn. Even as new discoveries accumulated week after week and month after month, demonstrating that these sequences regulated critical biological processes in ways scientists had never anticipated. The mystery that continues to captivate researchers today is not whether junk DNA has purpose, but rather how much purpose remains undiscovered, since scientists estimate that a significant portion of this non-coding DNA still has unknown functions waiting to be revealed through increasingly sophisticated genetic analysis, epigenetic research, and computational modeling, suggesting that our current understanding of the genome remains fundamentally incomplete, and that nature's elegance in utilizing every component may far exceed what we presently comprehend. Roughly 540 million years ago, during a geological period known as the Cambrian era, the fossil record reveals one of the most perplexing transitions in the history of life on Earth, when an extraordinary diversity of complex animal body plans appeared in the geological strata in what seems like a relatively compressed timeframe, a phenomenon that paleontologists and evolutionary biologists have termed the Cambrian explosion. And this sudden proliferation of complex life forms remains one of the most profound mysteries in science because the fossil record preceding this event shows relatively simple organisms like sponges and early multicellular creatures. Then suddenly we find evidence of trilobites, arthropods, mollusks, echinoderms, and countless other sophisticated animals with specialized body parts, sensory organs, and complex behavioral capabilities, all appearing within what amounts to perhaps 20 to 30 million years in geological time. The traditional Darwinian explanation suggests that evolution through natural selection should produce gradual changes over immense periods. Yet the Cambrian explosion appears to contradict this gradualist model by compressing the emergence of major animal body plans into what feels like a relatively instantaneous moment in deep time, and multiple competing theories attempt to explain this phenomenon, including changing ocean oxygen levels that may have allowed more complex metabolic processes, the evolution of predatory behavior that drove an arms race of adaptation, genetic innovations like the development of new gene regulatory networks that permitted greater body plan complexity, and environmental changes such as increased nutrient availability or climate fluctuations that created ecological opportunities for diversification. What makes this mystery particularly challenging is that we possess a relatively incomplete fossil record from this period, meaning we may be missing countless transitional forms that would clarify the progression from simple to complex life. Yet despite our incomplete knowledge, we have normalized the existence of this gap by continuing to teach it as a settled, if somewhat mysterious chapter in evolutionary history, when in fact the mechanisms driving such rapid diversification remain genuinely uncertain, and the persistence of this mystery, alongside our cultural acceptance of evolutionary theory, demonstrates how science can accommodate genuine unknowns while still maintaining confidence in overarching frameworks. Reflecting a balance between acknowledging what we definitively understand and remaining honest about the substantial questions that continue to perplex researchers studying the deep origins of animal diversity on our planet. 66 million years ago, the reign of the dinosaurs came to an abrupt and catastrophic end, yet the precise mechanisms of this extinction remain shrouded in scientific uncertainty and ongoing debate. The prevailing theory involves a massive asteroid impact near what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater and triggering a global cataclysm of unimaginable proportions. However, the exact sequence of events following impact remains poorly understood, with scientists unable to definitively explain whether dinosaurs perished primarily from the initial blast and heat radiation, from the subsequent tsunamis and earthquakes, from the months of darkness caused by impact-generated dust and soot blocking the sun, from acid rain and atmospheric chemical changes, or from some combination of these catastrophic factors working in concert. The fossil record shows that extinction was not instantaneous across all species, suggesting that certain dinosaurs may have survived for years or even decades after the impact before succumbing to environmental collapse, yet we lack clear evidence of what sustained them or ultimately doomed them. Paleontologists continue to investigate whether the impact alone was sufficient to cause total extinction, or whether other factors including massive volcanic activity, climate instability, and ecosystem disruption in the preceding millennia had already weakened dinosaur populations, making them vulnerable to the final blow. The puzzle deepens when considering why some creatures survived while others vanished, why birds evolved from theropod dinosaurs while their non-avian relatives died out completely, and how mammals so small and seemingly insignificant managed to persevere through conditions lethal to the dominant vertebrates of their time. We remain uncertain about the precise atmospheric composition during the impact's aftermath, the exact temperature fluctuations organisms experienced, the timeline of ecosystem recovery, and whether multiple extinction pulses occurred rather than a single event. Despite possessing sophisticated dating techniques, computer modeling, and extensive fossil collections, the scientific community still cannot fully reconstruct the sequence of doom that unfolded, leaving this catastrophic turning point in Earth's history as a compelling reminder of how much remains unknown about our planet's distant past. Recent discoveries of soft tissue preservation and chemical signatures in late Cretaceous fossils offer tantalizing new avenues for investigation. Yet interpreting these ancient molecular remnants requires developing entirely new methodologies that push the boundaries of paleontological science. While many animals possess an innate ability to sense the Earth's magnetic field, allowing migratory birds to navigate thousands of miles with stunning precision and sea turtles to return to their natal beaches across vast ocean distances, humans have long been considered deaf to this invisible force that permeates our planet. Yet in recent years, a growing body of scientific inquiry has begun to explore whether humans might possess a dormant or vestigial magnetic sense that we have simply failed to recognize or develop over countless generations of civilization. Researchers have documented cases of individuals who appear to possess an unusual sensitivity to directional information without relying on conventional sensory cues, and some studies suggest that our brains may contain magnetite crystals or proteins similar to those found in migratory animals, potentially positioned in areas like the inner ear or ethmoid bone near our olfactory system. The mechanism by which such a sense might function would involve specialized cells detecting minute variations in the Earth's magnetic field, transmitting this information to the brain as a form of directional awareness that operates largely below the threshold of conscious perception, much like our body's sense of proprioception guides our limbs through space without conscious effort. Despite these intriguing possibilities, the scientific community remains divided on whether humans truly possess a functional magnetic sense, or whether the evidence merely reflects random variation, wishful thinking, or experimental artifacts caused by subtle biases in study design. What fascinates us about this mystery is that even if humans once possessed this ability millions of years ago, we have somehow allowed it to atrophy or become so profoundly suppressed by our reliance on technological navigation and conscious spatial reasoning that we can no longer access it. And yet we continue searching for evidence of its existence, as though reclaiming this lost sense might reconnect us to our evolutionary past and the natural world we have increasingly insulated ourselves from. Some researchers have begun investigating whether practices like meditation or sensory deprivation might reawaken latent magnetic perception, while others speculate that certain individuals, particularly those with synesthesia or unusual neurological configurations, may retain stronger connections to this ancestral ability than the general population. If such a sense does exist within us, dormant and waiting, it would represent not a deficiency in human evolution, but rather a capability we voluntarily surrendered in exchange for the cognitive tools that built our civilizations. When an airplane encounters turbulence, passengers experience sudden jolts, unpredictable movements, and the sensation of falling, yet despite decades of meteorological advancement and computational power, we still cannot predict or fully understand turbulence with complete accuracy. Turbulence occurs when air masses of different temperatures, pressures, and velocities interact and create chaotic, swirling patterns that disrupt the smooth flow of air around an aircraft, and these disturbances can range from barely perceptible bumps to violent shaking that causes injury and structural stress. Commercial pilots navigate around known turbulence zones using weather reports and communication with other aircraft, but they constantly encounter unexpected patches of severe turbulence that appear without warning in seemingly clear skies. A phenomenon known as clear air turbulence that defies conventional detection methods. The mathematical problem underlying turbulence is extraordinarily complex, involving the Navier-Stokes equations, which describe fluid motion but become nearly impossible to solve precisely once turbulence develops, as the system becomes so sensitive to initial conditions that minuscule variations create dramatically different outcomes. What makes turbulence particularly perplexing is that we understand the basic physics, yet we cannot construct a complete theoretical framework that allows us to predict exactly where and when turbulence will occur or how severe it will be. Scientists recognize that turbulence involves cascade patterns where larger eddies break down into progressively smaller ones, dissipating energy as heat, but the transition point from laminar flow to turbulent flow remains probabilistic rather than deterministic. We have normalized our inability to predict turbulence by accepting it as an inevitable feature of flight, teaching pilots to navigate around it reactively rather than predictively, and passengers simply endure the experience as a necessary aspect of modern travel, despite the fact that this represents a significant gap in our scientific understanding of one of the most fundamental phenomena in physics. Yet this gap persists not from lack of effort, but from the inherent nature of turbulent systems themselves, chaotic systems where perfect prediction may be theoretically impossible, suggesting that a complete theory of turbulence might require us to fundamentally redefine what we mean by understanding and prediction in physics. Perhaps the most humbling aspect of this limitation is that turbulence occurs not only in Earth's atmosphere, but in oceans, stars, and the quantum realm itself, suggesting that our incomplete understanding of turbulence represents a gap that extends far beyond aviation into the fundamental architecture of how the universe. Deep within the mathematics of fluid dynamics lies one of the most deceptively simple yet profoundly unsolved problems in all of science, a mystery that has persisted for nearly 2 centuries despite its fundamental importance to everything from engineering bridges to predicting weather patterns to understanding how blood flows through our veins. The Navier-Stokes equations, formulated in the early 1800s, are a set of differential equations that describe how fluids move and behave under various forces and conditions, governing the motion of gases and liquids in ways that seem straightforward on their surface, but reveal themselves to be extraordinarily complex in their deeper mathematical structure. These equations work remarkably well in practice, allowing engineers to design aircraft and predict turbulence and simulate ocean currents with impressive accuracy. Yet mathematically speaking, we do not actually know whether smooth, physically reasonable solutions to these equations even exist for all initial conditions, or whether the equations might develop finite-time singularities where values become infinite in finite time. The logical mechanism behind this puzzle stems from the fact that while we can write down the equations that should govern fluid motion based on physical principles like conservation of mass and momentum, actually proving that these equations behave the way our physical intuition tells us they should requires navigating extraordinarily difficult mathematical terrain involving functional analysis, partial differential equations, and nonlinear dynamics in ways that have eluded the world's greatest mathematicians. The persistence of this unsolved problem is particularly striking because it is so fundamental to our understanding of the natural world, and because we have developed workarounds and approximations that allow us to use these equations practically despite our theoretical ignorance, creating a strange situation where we can engineer based on mathematics we do not fully understand, where we trust equations we cannot prove, and where perhaps the most important unsolved problem in applied mathematics continues to quietly underpin countless technologies and scientific endeavors that we depend upon every single day. Yet this paradox, that we can predict the behavior of a hurricane or design a more efficient airplane engine without fully understanding the mathematical foundations beneath our calculations, suggests that sometimes practical knowledge and theoretical proof must follow different paths, and that the Navier-Stokes equations may represent a fundamental limit to what mathematics can guarantee about the natural world, even as physics marches confidently forward. Deep within the architecture of computer science and mathematics lies one of the most profound unsolved questions in human knowledge, a problem so fundamental that solving it would reshape our understanding of computation itself, and the question is deceptively simple to state, yet has resisted resolution for decades. Is P equal to NP? To understand what this means, Imagine two distinct categories of problems that computers must solve. The first category, called P, which contains all problems that a computer can solve quickly, meaning that a solution can be found and verified in what mathematicians call polynomial time, essentially a reasonable amount of computational steps that doesn't explode exponentially as the problem size grows. The second category, NP, contains all problems for which a proposed solution can be checked quickly. Even if finding that solution originally took an extraordinarily long time, imagine if someone handed you the answer to a complex mathematical puzzle and you could verify it was correct in minutes, but finding that answer yourself took years of searching through possibilities. The deep mystery is whether these two categories are actually the same thing, whether every problem whose solution can be verified quickly can also be solved quickly, or whether they are fundamentally different, with NP problems representing a genuinely harder class of challenges that no algorithm could ever efficiently solve. The implications of this question are staggering because many real-world problems that affect cryptography, optimization, and artificial intelligence are believed to be NP problems. If P equals NP, then every secure encryption system protecting financial transactions and private communications worldwide could potentially be broken efficiently. Every optimization challenge that currently requires heuristic guessing could be solved perfectly. And the entire landscape of computational possibility would transform. Yet despite countless brilliant mathematicians and computer scientists dedicating their careers to this problem, despite millions of dollars offered as prize money for a solution, despite the question being formally posed in 1971, the answer remains tantalizingly out of reach, existing in a strange liminal space where most scientists believe P does not equal NP based on intuition and evidence, yet no one has managed to prove it rigorously. The problem persists in this state of uncertainty because the question sits at the intersection of logic and computation in ways that seem to elude the mathematical tools we currently possess. And perhaps this mystery endures because the answer might require an entirely new mode of mathematical thinking that humanity has not yet conceived, a framework that could unlock not just P versus NP, but entire categories of problems. Deep within the landscape of pure mathematics exists a conjecture so deceptively simple in its statement, yet so profoundly complex in its implications that it has resisted proof for nearly 2 centuries, captivating the minds of the world's greatest mathematicians and remaining one of the 7 Millennium Prize problems worth $1 million to whoever can solve it. The Riemann hypothesis, proposed by Bernhard Riemann in 1859, concerns itself with the distribution of prime numbers, those fundamental building blocks of arithmetic that cannot be divided evenly by any number except one in themselves. And it suggests that all non-trivial zeros of the Riemann zeta function must lie on a single vertical line in the complex plane known as the critical line. To understand the psychological grip this problem holds, one must recognize that mathematicians have verified the hypothesis for trillions upon trillions of zeros, each calculation reinforcing confidence in its truth. Yet this empirical evidence cannot constitute a proof, for mathematics demands absolute logical certainty rather than statistical likelihood. The mechanism behind the hypothesis's persistence lies in the intersection of 3 powerful human tendencies: our attraction to elegant patterns and symmetries that suggest underlying truth, our frustration with problems that seem almost within reach, yet perpetually slip beyond our grasp, and our faith in the deep connection between abstract mathematical structures and the physical universe itself. The Riemann zeta function itself emerges from the study of infinite series and connects intimately to the distribution of prime numbers through the Euler product formula, creating a bridge between seemingly disparate mathematical domains that suggests something profound lies at the foundation of number theory. What makes this conjecture particularly haunting is that mathematicians have developed entire theories and built substantial mathematical edifices upon the assumption that Riemann was correct, proceeding as if the hypothesis were proven truth, creating a strange situation where large portions of modern mathematics rest upon an unverified foundation. The persistence of this unsolved problem speaks to how we have normalized mathematical uncertainty in certain domains, accepting that some questions may never be answered within our current frameworks, yet we continue forward anyway, building knowledge upon provisional assumptions that may ultimately require reconstruction if the hypothesis proves false. Yet perhaps this very vulnerability, mathematics advancing on uncertain ground, reveals something essential about how human knowledge grows, not through perfect certainty alone, but through bold conjectures that organize our understanding and invite us toward deeper truths. In the year 1742, a Prussian mathematician named Christian Goldbach wrote a letter to the Swiss mathematician Leonhard Euler proposing a deceptively simple idea that would come to haunt the mathematical world for nearly 3 centuries without resolution. Goldbach observed that every even number greater than 2 could apparently be expressed as the sum of exactly 2 prime numbers, those fundamental building blocks of mathematics that can only be divided by 1 and themselves. At first glance, this seems like a straightforward observation that ought to yield to rigorous proof, yet despite the combined efforts of some of history's greatest mathematical minds and the computational power of modern supercomputers testing trillions upon trillions of cases, no one has ever succeeded in proving or disproving this elegant conjecture. The sheer simplicity of the statement stands in remarkable contrast to its apparent unsolvability, creating a peculiar tension that attracts mathematicians the way mysteries attract the curious. The conjecture works beautifully in practice. Take the number 10 and you can express it as 5 plus 5. Take 24 and it becomes 5 plus 19. Take 100 and it becomes 3 plus 97. The pattern holds across every single example that has ever been tested, from small numbers that children can verify by hand to astronomical numbers that require the processing power of entire data centers. Yet mathematics operates according to a principle that no matter how many examples confirm a pattern, only a complete proof establishes absolute truth. This distinction between empirical observation and logical demonstration represents one of the deepest principles of mathematical thinking, and it is precisely this principle that makes Goldbach's conjecture so stubbornly resistant to resolution. What makes this mystery particularly fascinating is how it has normalized the existence of mathematical truths that we cannot prove, forcing mathematicians to accept that certainty itself might possess limits within formal systems of logic and reasoning. Gödel's incompleteness theorems would later formalize this unsettling possibility, suggesting that some statements, perhaps even Goldbach's conjecture itself, might be true yet fundamentally unprovable within any consistent mathematical system, a revelation that transformed this simple observation about even numbers into a profound meditation on the nature of mathematical reality itself. The conjecture thus stands as a humbling reminder that mathematics, for all its precision and power, contains depths we have yet to fathom, a frontier where the simplest questions sometimes demand answers that may lie forever beyond our reach. Consider a simple mathematical operation that has perplexed mathematicians for nearly a century. Take any positive whole number, and if it is even, divide it by 2, but if it is odd, multiply it by 3 and add 1, then repeat this process indefinitely with whatever number results. The conjecture proposes that no matter which positive integer you begin with, you will eventually reach the number 1, and once you arrive at 1, the sequence will cycle endlessly through 1, 4, 2, and back to 1 again. This deceptively straightforward premise has become one of mathematics' most haunting unsolved problems, baffling brilliant minds across decades despite being simple enough for a high school student to understand and verify. The psychological mechanism underlying this mystery lies in the gap between computational verification and mathematical proof. Computers have tested trillions upon trillions of numbers, and every single one eventually reaches 1, yet mathematicians cannot explain why this pattern holds universally or construct a rigorous proof that it must always be true. The human mind struggles with this peculiar circumstance because it violates our intuitive expectation that empirical evidence should eventually satisfy intellectual curiosity. Yet here we find ourselves unable to bridge the chasm between what appears to be universally true and what we can prove must be true. What makes the Collatz conjecture so mathematically unsettling is that it belongs to a category of problems that seem simple on their surface, yet conceal profound complexity, touching upon fundamental questions about the nature of numbers and the limits of what mathematical systems can demonstrate. Over the decades, the conjecture has persisted in academic literature and popular mathematical imagination precisely because of this tantalizing quality. It invites endless attempts at proof, despite remaining stubbornly resistant to resolution, suggesting that perhaps the underlying truth relates to deeper mathematical principles we have not yet discovered, or perhaps even that some truths about numbers simply cannot be proven within our current mathematical frameworks. The Collatz conjecture thus serves as a humbling reminder that mathematics, despite its reputation for absolute certainty, contains islands of mystery where empirical patterns outpace our theoretical understanding. A phenomenon that has inspired mathematicians to develop entirely new proof techniques and mathematical frameworks in hopes of eventually illuminating what remains hidden in these deceptively simple sequences. In this sense, the Collatz conjecture exemplifies how mathematics itself evolves through confrontation with its own mysteries, pushing mathematicians toward innovations that ultimately enrich the entire discipline far beyond any single. Among all the mathematical mysteries that have captivated human minds for centuries, few are as elegantly simple yet profoundly perplexing as the distribution of prime numbers, those integers greater than one that can only be divided evenly by themselves and one. Throughout history, mathematicians have observed that prime numbers appear scattered across the number line in what seems like a chaotic, almost random fashion, yet simultaneously exhibiting peculiar regularities that suggest some hidden underlying order waiting to be discovered. The twin prime conjecture proposes that infinitely many pairs of primes exist that differ by exactly 2, such as 11 and 13 or 29 and 31, yet despite extensive computational searches and theoretical investigations, this tantalizing pattern remains unproven. Equally mysterious is the Goldbach conjecture, which suggests that every even number greater than 2 can be expressed as the sum of exactly 2 prime numbers, a statement verified computationally for astronomers-level figures, yet without rigorous mathematical proof. The gaps between consecutive primes seem to follow no discernible formula, sometimes appearing after just 2 numbers, sometimes after dozens or hundreds, creating an apparent randomness that contradicts the deterministic nature of the definition itself. Mathematicians have devoted countless hours to visualizing these patterns through spirals, density maps, and sophisticated computational analyses, revealing tantalizing geometric arrangements that hint at organization without ever quite revealing the complete architecture. This persistence of mystery endures not because mathematics lacks rigor, but precisely because prime numbers occupy a peculiar position in the landscape of numerical reality, fundamental enough to structure much of cryptography and modern security systems, yet resistant enough to complete understanding that they continue humbling even the most brilliant minds, reminding us that some aspects of abstract reality maintain their enigmatic quality regardless of how deeply we investigate. Perhaps this is precisely why prime numbers continue to inspire wonder. They represent a frontier where mathematics meets mystery, where human curiosity encounters the boundaries of what we can prove, inviting each new generation of mathematicians to contribute their own insights to an ancient and unfinished quest. From the Riemann hypothesis, which relates prime distribution to the zeros of a complex function, to emerging computational methods that detect new patterns in previously unseen ranges of numbers, each breakthrough simultaneously opens new questions, suggesting that the ultimate nature of prime distribution may belong to a deeper layer of mathematical reality than we currently possess the tools to access. In mathematics, perfect numbers represent one of the oldest and most peculiar mysteries, a category so rare and strangely distributed that mathematicians have spent millennia studying them without reaching definitive answers. A perfect number is defined as a positive integer that equals the sum of its proper divisors, the numbers that divide evenly into it excluding itself, which means 6 is the first perfect number because 1 plus 2 plus 3 equals 6, and 28 is the second because 1 plus 2 plus 4 plus 7 plus 14 equals 28. What makes this phenomenon genuinely mysterious is not merely that perfect numbers exist, but rather that they appear to follow patterns that seem deliberately arranged by some hidden mathematical principle that remains frustratingly beyond our comprehension. The distribution of perfect numbers follows such an extraordinarily sparse pattern that mathematicians have discovered only 51 of them despite centuries of intensive searching, and these numbers increase not gradually but explosively in size, with the fifth perfect number containing more than 8,000 digits, a fact that suggests some profound underlying structure governs their appearance. The Euclid-Euler theorem established that every even perfect number corresponds to a Mersenne prime, a prime number of the form 2 to the power of p minus 1, creating a tantalizing connection between two separate mathematical concepts that should theoretically allow us to predict where perfect numbers will appear. Yet oddly, this knowledge has done little to illuminate why this connection exists or why it works with such mysterious precision. Mathematicians have noticed that perfect numbers seem to grow at rates that defy easy prediction, clustering in particular ranges before vanishing into computational silence, and whether odd perfect numbers exist at all remains entirely unknown despite mathematical investigation spanning over 2,000 years. The psychological mechanism driving continued research into perfect numbers stems from our deep human need to find order within apparent randomness, to discover that what seems scattered and inexplicable actually follows hidden rules we simply have not yet decoded, transforming mathematical curiosity into something approaching spiritual yearning. We have normalized this unsolved mystery by compartmentalizing it, treating perfect numbers as an abstract puzzle rather than confronting the genuinely unsettling reality that mathematics, humanity's most rigorous logical system, contains gaps and patterns we cannot fully understand or predict, suggesting that perhaps our universe itself contains depths of organization that remain permanently beyond reach. When a bubble collapses within a liquid after being exposed to sound waves, something remarkable occurs that scientists have struggled to fully understand for decades. The bubble emits a brief flash of light. This phenomenon, known as sonoluminescence, was first observed in the 1930s, yet despite nearly a century of investigation, the precise mechanism responsible for generating this light remains one of the most perplexing mysteries in modern physics. When sound waves of sufficient intensity pass through a liquid containing microscopic bubbles, those bubbles experience rapid expansion and contraction cycles, oscillating at frequencies that can reach thousands of times per second. During the collapse phase, the bubble compresses with tremendous force, and in those final moments before implosion, the interior gas reaches extraordinarily high temperatures and pressures that should theoretically produce the conditions necessary for light emission. What makes this phenomenon so scientifically frustrating is that multiple competing theories attempt to explain it, yet none commands universal acceptance within the scientific community. Some researchers propose that the extreme conditions during bubble collapse approach the temperatures of stellar interiors, potentially triggering nuclear fusion reactions or exotic quantum effects. Others suggest that the light results from molecular excitation and subsequent photon emission as atoms within the compressed gas release energy. Still others invoke the possibility of Cherenkov radiation, where charged particles travel faster than light through the medium and emit electromagnetic radiation in the process. The mystery deepens when one considers that the intensity and characteristics of the emitted light seem to resist complete explanation through any single proposed mechanism. Experiments have produced sonoluminescent bubbles under controlled laboratory conditions, revealing light emissions at wavelengths ranging from ultraviolet to visible spectrum, yet the energy budget simply does not seem to align perfectly with any conventional physics model. Despite decades of research involving sophisticated equipment and brilliant minds devoted to understanding this phenomenon, sonoluminescence continues to generate debate and disagreement about its fundamental cause, making it a genuinely unsolved mystery that bridges the gap between everyday physical phenomena and the theoretical extremes of our understanding. Recent advances in spectroscopic analysis and high-speed imaging have enabled researchers to observe sonoluminescent events with unprecedented detail. Yet each new discovery seems to raise as many questions as it answers, suggesting that the true explanation may require entirely novel physics or a synthesis of multiple mechanisms working in. Imagine filling two identical containers with water, one at room temperature and one heated to nearly boiling, and then placing both into a freezer at the same time. According to conventional physics, the hot water should take longer to freeze because it must first cool down to match the temperature of the cold water before the actual freezing process can begin. Yet for centuries, observations have suggested something counterintuitive occurs. The hot water sometimes freezes faster than the cold water, a phenomenon known as the Mpemba effect, named after Tanzanian student Erasto Mpemba, who documented and studied this curious observation in the 1960s, though similar accounts had been noted since the time of Aristotle himself. The effect appears to contradict the basic laws of thermodynamics, those fundamental principles that govern heat transfer and energy distribution in our universe, creating a genuine puzzle that continues to perplex scientists and remains incompletely understood even in our modern era. Several competing hypotheses have emerged to explain why hot water might occasionally freeze faster than cold water, and the truth likely involves a combination of these mechanisms working together in subtle and complex ways. Some researchers propose that convection currents in hot water may be more vigorous, allowing heat to escape more efficiently from the surface, while others suggest that evaporation from hot water reduces its mass more significantly, meaning less material actually needs to freeze. Additional theories invoke the role of dissolved gases that escape from heated water more readily, or the formation of different crystal structures when water cools from higher temperatures. The effect also depends heavily on the specific conditions of the experiment, including the exact shape and material of the containers, the precise temperature differences involved, the ambient humidity, and the particular freezer environment being used. When researchers attempt to replicate the Mpemba effect under carefully controlled laboratory conditions, results remain frustratingly inconsistent and unpredictable, with some experiments confirming the effect while others fail to demonstrate it entirely. This inconsistency suggests that multiple overlapping factors contribute to the phenomenon, making it difficult to isolate and study any single mechanism in isolation. The Mpemba effect persists in our collective consciousness as a genuine scientific mystery precisely because it challenges our intuitive understanding of how the world should work. And despite decades of investigation, no single unified explanation has achieved universal acceptance within the scientific community. In laboratories around the world, scientists have discovered that certain materials, when cooled to extraordinarily low temperatures, suddenly lose all electrical resistance and expel magnetic fields in a phenomenon called superconductivity. Yet the mechanism behind high-temperature superconductivity, which occurs at temperatures far warmer than traditional superconductors, though still requiring cooling with liquid nitrogen, remains one of the most perplexing unsolved mysteries in condensed matter physics. When these ceramic materials and copper oxide compounds are chilled below their critical temperature, electrons appear to move through the material without any friction whatsoever, creating perfect conductors that can maintain electrical currents indefinitely without any power input, a behavior that defies the conventional understanding of how electrons interact with atomic lattices. The conventional theory of superconductivity, developed by Bardeen, Cooper, and Schrieffer, explains low-temperature superconductivity through the formation of electron pairs called Cooper pairs that move together without scattering. Yet this theory fails dramatically when applied to high-temperature superconductors, where the mechanism seems fundamentally different and the electrons pair up in ways that our current mathematical models cannot adequately describe. Researchers have proposed numerous explanations over the past 4 decades, suggesting that exotic quantum interactions, magnetic fluctuations, or entirely novel pairing mechanisms might be responsible. Yet no single theory has achieved consensus or explained all the observed properties, leaving physicists studying the internal structure of these materials through advanced spectroscopy and experiments that reveal tantalizing clues, but never quite unveiling the complete picture. The persistence of this mystery is particularly striking given the enormous practical potential, as understanding high-temperature superconductivity could revolutionize technology by enabling more efficient power transmission, faster computers, and improved medical imaging, motivations that have driven billions of dollars in research funding across multiple nations and institutions. Yet despite decades of intensive investigation, employing increasingly sophisticated experimental techniques and computational approaches, the fundamental question of how and why electrons in these materials can achieve perfect conductivity at relatively high temperatures remains stubbornly unanswered, suggesting that nature operates according to principles in these quantum regimes that we have not yet discovered or imagined. And that solving this mystery may require entirely new conceptual frameworks rather than merely refinements to existing theories. Superconductivity represents one of the most tantalizing promises in modern physics, a state of matter where electrical current flows through a material with absolutely zero resistance, creating effects so profound that they seem to defy our everyday understanding of how the world works. For decades, scientists have observed superconductivity occurring in various materials, but only when cooled to extraordinarily low temperatures, typically near absolute zero or within a few degrees of it, requiring expensive and energy-intensive cooling systems using liquid helium or liquid nitrogen to maintain these conditions. The dream that has captivated physicists and engineers alike is the possibility of achieving superconductivity at room temperature, around 20 degrees Celsius, which would fundamentally transform technology and energy infrastructure across the entire globe. Imagine power transmission lines that lose absolutely no energy to resistance, magnetic levitation trains operating without the burden of constant cooling, medical imaging devices that function without massive refrigeration systems, and quantum computers that could operate in normal laboratory conditions rather than in specialized facilities. The theoretical framework behind superconductivity involves the behavior of electrons forming Cooper pairs that move through the material's lattice structure without scattering, creating this perfect state of zero electrical resistance. Yet despite more than a century of intensive research, since the phenomenon was first discovered in 1911, room temperature superconductors remain firmly in the realm of elusive scientific goals rather than established reality. Sporadic claims have emerged over the years, most notably in 2020 and 2023, when researchers announced breakthroughs that seemed to promise room temperature superconductivity. Yet each of these claims has faced intense scrutiny, reproduction difficulties, and ultimately skepticism from the broader scientific community. The persistence of this mystery reflects a peculiar psychological state within science itself, where the potential payoff is so tremendous that researchers continue pursuing it despite decades of failure, and where preliminary reports can generate worldwide excitement even as the fundamental gap between theory and experimental reality remains stubbornly wide, suggesting that room temperature superconductors may require either revolutionary new materials yet to be discovered or entirely new physical principles that we have not yet conceived. What makes this pursuit particularly compelling is that nature itself may already possess the answer. Some scientists speculate that room temperature superconductivity could exist in exotic materials like. In March of 1989, two electrochemists named Martin Fleischmann and Stanley Pons announced they had achieved nuclear fusion at room temperature inside a small tabletop apparatus, a discovery that would have fundamentally altered our understanding of physics and provided humanity with virtually unlimited clean energy. Yet their announcement sparked one of the most contentious scientific controversies of the modern era, dividing laboratories and institutions across the globe. Their experimental setup was deceptively simple. They used a palladium electrode immersed in deuterium oxide, applying an electrical current to initiate what they claimed was a fusion reaction that released excess heat far beyond what conventional chemistry could explain, and they presented their findings with remarkable confidence, suggesting that cold fusion could revolutionize energy production within years rather than decades. The scientific community responded with intense scrutiny, and while some laboratories reported similar results, many prominent institutions could not reproduce the findings with any consistency, leading to accusations of experimental error, faulty measurements, and in some cases, allegations of deliberate misrepresentation of data. The psychological mechanism underlying cold fusion's persistent appeal lies in its representation of the ultimate scientific promise. The idea that a simple, elegant solution to humanity's greatest challenges might exist just beyond our current understanding, accessible not to massive government-funded facilities, but to small teams of dedicated researchers working in modest laboratories. This narrative carries profound emotional weight because it suggests that revolutionary breakthroughs need not require vast infrastructure or decades of theoretical preparation, that the next great advance might emerge unexpectedly from anywhere, and that established scientific hierarchies might occasionally overlook transformative discoveries due to institutional biases and conventional thinking. Despite the overwhelming consensus among mainstream physicists that cold fusion at room temperature remains thermodynamically implausible and that no reproducible, convincing evidence of the phenomenon has ever been demonstrated according to rigorous scientific standards, researchers continue investigating related phenomena under various names and frameworks, keeping the possibility alive in the margins of legitimate scientific discourse. The persistence of cold fusion as a concept reflects our collective yearning for a transformative solution to energy problems combined with a lingering distrust of institutional science, creating a space where the impossible maintains a ghostly plausibility, forever suspended between hope and dismissal, neither fully dead nor authentical. The M-drive represents one of the most contentious and perplexing cases of modern physics, a device that allegedly violates the most fundamental law of motion while simultaneously attracting serious scientific attention and institutional funding. In 2001, a British inventor named Roger Scheuer patented a concept for a propulsion system that supposedly generates thrust without ejecting any propellant, fundamentally contradicting Newton's third law, which states that for every action there must be an equal and opposite reaction. The device operates by bouncing microwave radiation around an asymmetrical metal chamber, and according to Scheuer's claims, this creates a net force that should theoretically allow a spacecraft to accelerate without fuel, revolutionizing space travel entirely. What makes the M-drive particularly fascinating from a scientific perspective is not merely that it violates established physics, but that when researchers from various institutions including NASA's EagleWorks laboratory conducted experiments, some of them reported detecting small amounts of thrust, enough to spark genuine debates within the scientific community about whether existing physical models might be incomplete or whether experimental error was occurring. The psychological mechanism underlying the M-drive's persistence involves several interconnected factors, including the profound human desire to achieve breakthrough technologies, the emotional appeal of a solution to one of space exploration's greatest challenges, and the natural scientific impulse to investigate anomalies rather than dismiss them outright. The device resonates with our deepest hopes for transformation and transcendence, offering an almost mythological promise of infinite possibility, and this emotional resonance helps explain why intelligent researchers have invested time studying it despite the theoretical objections. Yet despite decades of research and multiple experimental attempts, no conclusive evidence has emerged demonstrating that the M-drive actually works as proposed, and most mainstream physicists attribute any observed effects to measurement errors, thermal artifacts, or electromagnetic interactions with Earth's magnetic field rather than genuine propulsion. The M-drive persists in scientific discourse not because compelling evidence supports it, but because the allure of revolutionary technology, combined with the genuine inability to absolutely prove negative claims, creates a space where doubt can perpetually reside, where we continue investigating the impossible simply because we have not yet achieved absolute certainty of its impossibility. When spacecraft travel through space and make close approaches to planets, they gain or lose velocity depending on gravitational interactions with those massive celestial bodies, a phenomenon perfectly explained by Newtonian mechanics and general relativity. However, beginning in the 1990s, scientists began noticing something deeply perplexing occurring during planetary flybys of various unmanned probes, particularly with NASA missions like Galileo, NEAR Shoemaker, Cassini, and Rosetta. After these spacecraft made their closest approaches to Earth or other planets during gravity-assist maneuvers, their velocities deviated slightly from what calculations predicted, showing unexpected acceleration or deceleration that shouldn't have occurred according to established physics. The discrepancy was minute, typically only a few millimeters per second, yet it was consistent and measurable through Doppler shift analysis of radio signals transmitted back to Earth. This became known as the flyby anomaly, a modest but persistent mystery that challenges our understanding of gravitational mechanics at the most fundamental level. The situation reveals something troubling about the relationship between observation and theory. Scientists have examined every conceivable explanation within conventional frameworks: measurement errors, relativistic effects not yet accounted for, atmospheric drag, solar radiation pressure, and unmodeled gravitational influences from nearby celestial bodies. Yet none of these conventional explanations fully resolves the anomaly across all the different spacecraft and planetary encounters studied. Some researchers have speculated that modifications to gravitational theory itself might be necessary, though such radical suggestions remain highly controversial within the scientific establishment. The persistence of this small but measurable deviation suggests that either our instruments are somehow systematically biased in ways we don't understand, or there exists some genuine physical phenomenon that our current models simply fail to capture. What makes the flyby anomaly particularly unsettling is how it persists despite decades of scrutiny by brilliant scientists armed with sophisticated instruments and computational power beyond what previous generations could imagine. The anomaly remains neither fully explained nor fully dismissed, existing in an uncomfortable intellectual space where it cannot be ignored but cannot be integrated into existing theory. It continues to appear in mission data, quietly suggesting that the universe harbors secrets in spaces we thought we had thoroughly mapped. Deep within the molecular machinery of living organisms, there exists a realm where the classical laws of physics that govern our everyday experience seem to break down entirely, where particles behave in ways that defy our intuitive understanding of how the world should work, and where quantum effects, phenomena once thought to exist only in the abstract theoretical domain of particle physics, appear to play a functional role in biological processes that have evolved over millions of years. Scientists have discovered tantalizing evidence that quantum tunneling, the phenomenon where particles pass through energy barriers that should be insurmountable according to classical physics, may be responsible for enabling certain enzymatic reactions to occur at rates far faster than conventional chemistry would predict, suggesting that the very machinery of life may depend upon quantum mechanical principles to function efficiently. Photosynthesis, the process by which plants and some bacteria convert light into chemical energy with remarkably high efficiency, demonstrates quantum coherence effects, where energy appears to explore multiple pathways simultaneously before settling on the most efficient route, a behavior that should not be possible if biological molecules behaved like classical objects. Yet somehow natural selection has apparently optimized these systems to harness quantum mechanical advantages. Similarly, the ability of migratory birds to navigate across thousands of miles may rely upon quantum entanglement effects in proteins within their eyes, allowing them to sense the Earth's magnetic field through quantum mechanical interactions that remain poorly understood despite decades of investigation. The persistent mystery lies in how these delicate quantum effects can survive in the warm, wet, chaotic environment of biological cells, where random thermal motion should destroy such fragile quantum states almost instantaneously. Yet evolution appears to have developed sophisticated protective mechanisms that shield these quantum processes from decoherence long enough for them to serve meaningful biological functions. We have normalized this cognitive dissonance by acknowledging that quantum biology remains an emerging frontier, one where genuine scientific evidence suggests that life has found ways to exploit the quantum world, even though the precise mechanisms, the evolutionary pressures that selected for these capabilities, and the full extent of their biological importance remain among the deepest unsolved questions in modern science. Recent investigations into olfaction suggest that quantum tunneling may enable our sense of smell to discriminate between molecularly similar compounds, while theoretical models propose that quantum effects could play roles in DNA mutation rates, enzyme. The concept of mitochondrial Eve represents one of the most fascinating yet frequently misunderstood conclusions in human genetics, referring to the most recent common maternal ancestor of all living humans based on mitochondrial DNA analysis. Yet the accuracy and implications of this scientific model remain shrouded in considerable uncertainty and popular misconception. When scientists first traced mitochondrial DNA backwards through maternal lineages across diverse human populations, they calculated that this theoretical ancestor lived somewhere between 50,000 and 200,000 years ago, a timeframe that seemed to provide a clear evolutionary narrative about human origins and dispersal. But the methodology underlying these calculations relies on numerous assumptions about mutation rates, population sizes, and genetic diversity that may not hold true across all human groups and all periods of evolutionary history. The fundamental mechanism driving our confidence in mitochondrial Eve comes from the elegant simplicity of maternal inheritance, since mitochondria are passed almost exclusively through the mother, creating an unbroken chain of genetic transmission that theoretically allows us to trace back to a single female ancestor. Yet this same mechanism also creates serious blind spots, because it ignores the vast majority of the human genome and cannot account for complex demographic patterns. Selection pressures, or the possibility that multiple maternal lineages may have existed simultaneously before convergence, makes this mystery particularly persistent in scientific and popular discourse, is how the concept has become normalized as definitive truth, despite the reality that mitochondrial Eve was never a single isolated woman, but rather a probabilistic mathematical construct representing the most recent point of coalescence in maternal lineage trees. and because the media and even some scientists have simplified this concept into an almost mythological figure of human ancestry, creating a false impression of certainty where significant ambiguity actually exists. Furthermore, the accuracy of molecular clock estimates used to date mitochondrial Eve has been repeatedly challenged by new research suggesting that mutation rates vary considerably across different populations, and may have been different in ancestral humans than in modern populations, meaning that dates calculated from genetic data alone could be substantially inaccurate. Yet these revised dates are rarely promoted with the same enthusiasm as the original conclusions, allowing the earlier estimates to persist in popular understanding long after being questioned by specialists in the field. Throughout Earth's history, life has experienced several catastrophic events where vast numbers of species vanished in relatively short periods of geological time, and these mass extinctions follow patterns so mathematically consistent that they have become one of the most perplexing mysteries in paleontology and evolutionary biology. The fossil record reveals that approximately 5 major extinction events have occurred over the past 500 million years, with the most famous being the Cretaceous-Paleogene extinction that eliminated the dinosaurs roughly 66 million years ago. Yet what fascinates scientists most is not simply that these extinctions happened, but rather that they appear to follow rhythmic cycles and mathematical patterns that suggest an underlying mechanism we have yet to fully comprehend. Researchers have proposed numerous explanations ranging from asteroid impacts and massive volcanic eruptions to changes in ocean chemistry and atmospheric composition. And while some extinction events do correlate with known catastrophic events like the Chicxulub impact in Mexico, many others lack any obvious external trigger that would adequately explain the sudden loss of such enormous numbers of species across diverse habitats and ecological niches. The psychological mechanism that keeps scientists engaged with this mystery stems from our deep human need to find order and predictability in chaos. Because if these extinctions truly follow mathematical patterns or cycles, it suggests that some underlying universal principle governs the rise and fall of life itself. And this notion of cosmic regularity appeals to our fundamental desire to understand the universe as governed by discoverable laws rather than random chance. Despite decades of research involving sophisticated computer modeling, detailed stratigraphic analysis, and increasingly precise radiometric dating techniques, we still cannot definitively explain why certain extinctions appear to occur at regular intervals, or why the selectivity of these events varies so dramatically, with some extinctions preferentially eliminating certain groups while leaving others relatively unscathed. And this uncertainty persists even as we have normalized the basic facts of mass extinction into our understanding of Earth's biological history. The mystery endures partly because the very timescales involved render direct observation impossible, yet partly also because accepting that we do not fully understand the mechanisms governing planetary-scale biological catastrophe remains uncomfortable for a species that prides itself on scientific mastery and predictive capability. Deep beneath the Earth's surface, the planet's crust is divided into massive sections called tectonic plates that constantly move and shift, yet scientists remain genuinely uncertain about what precisely initiates and sustains these colossal movements that reshape our world. We understand the mechanics reasonably well: convection currents in the mantle, the density differences between oceanic and continental crust, the push and pull of spreading ridges and subduction zones, the friction and resistance encountered along fault lines. All of these contribute to plate motion and help explain how plates continue moving once they have already begun their journeys. However, the fundamental trigger that first set these plates in motion remains one of geology's deepest mysteries, a question that sits at the very foundation of our understanding of planetary dynamics. When Earth formed approximately 4.5 billion years ago, the planet was far hotter, and the crust may have been too warm and plastic to form distinct, separate plates in the way we observe them today. Yet somehow, as the planet cooled, rigid plates emerged and began their endless dance of collision and separation. Some researchers propose that the initial trigger involved the cooling and solidification of the crust into brittle, fractured segments, while others suggest that impacts from planetary-scale collisions during Earth's formation provided the energy and disruption necessary to fragment the lithosphere into discrete plates that could move independently. The challenge lies in the fact that we cannot directly observe this ancient process, cannot recreate the conditions of the early Earth with perfect accuracy, and must piece together our understanding from indirect evidence. The composition of ancient rocks, the magnetic signatures frozen within them, the patterns of continental distribution across different geological epochs. What makes this mystery particularly vexing is that plate tectonics, once initiated, appears to be a self-sustaining system that maintains and perpetuates itself through the heat engine of the planet's interior. Yet the precise mechanism that first wound this planetary clock remains tantalizingly beyond our complete comprehension, reminding us that even the most fundamental processes shaping our world still hold secrets we have yet to fully unravel and understand. Recent advances in studying other terrestrial planets like Venus and Mars, where plate tectonics either never developed or ceased billions of years ago, offer intriguing comparative insights that might illuminate what conditions on early Earth were uniquely conducive to initiating and sustaining this planetary-scale process, suggesting that the trigger may have involved a delicate convergence of factors rather than a single catastrophic. Deep beneath our feet, at depths that no human has ever reached, lies one of the most fundamental mysteries of our planet, the precise composition and structure of Earth's core. We know that our planet possesses a solid inner core and a liquid outer core, together comprising the innermost layer of our world. Yet despite centuries of scientific investigation and increasingly sophisticated technological tools, significant uncertainties remain about what exactly these regions contain and how they behave. Scientists have constructed their understanding primarily through indirect methods, studying seismic waves generated by earthquakes that travel through the planet's interior, analyzing the behavior of Earth's magnetic field, and examining meteorite compositions as proxies for our planet's formation. These methods have revealed that the core is predominantly composed of iron and nickel, with smaller quantities of lighter elements such as sulfur, oxygen, and possibly potassium. Yet the precise proportions of these elements, the way they interact under the extreme pressures and temperatures of the core environment, and the exact mechanisms that drive the convection currents responsible for generating Earth's protective magnetic field remain subjects of considerable scientific debate and investigation. The psychological mechanism behind our acceptance of this uncertainty stems from the simple reality that Earth's core exists in a realm fundamentally inaccessible to direct human observation and measurement, operating under physical conditions that cannot be fully replicated in laboratory settings, which creates an inherent explanatory gap between what we theorize and what we can verify with absolute certainty. We have normalized this gap by placing trust in indirect scientific methods and mathematical modeling, accepting that some knowledge of our world must be inferred rather than observed directly. Yet this acceptance carries with it a quiet acknowledgement that our understanding of Earth's innermost domain remains incomplete and subject to revision as new evidence emerges and technology advances further. Recent discoveries, such as evidence of a solid inner core within the liquid outer core and the detection of unexpected chemical reactions occurring under extreme pressures, demonstrate how new instrumental capabilities continually reshape our understanding of what lies beneath, reminding us that the story of Earth's core remains unfinished and that humility in the face of planetary mysteries is perhaps the most scientifically grounded position we can adopt. The discovery of iron snow falling through the outer core, or the possibility that silicon comprises a larger fraction than previously thought, exemplifies how each new finding invites fresh questions rather than providing final answers. The formation of Earth's moon remains one of the most compelling unsolved mysteries in planetary science, with multiple competing theories offering different explanations for how our celestial companion came to exist in its current orbit and configuration. The most widely accepted hypothesis among scientists is the giant impact theory, which proposes that approximately 4.5 billion years ago, a Mars-sized planetary body collided with the early Earth in a catastrophic encounter that fundamentally altered the trajectory of both worlds. Yet despite decades of computational modeling and analysis, significant uncertainties persist regarding the precise mechanics of this collision, the composition of the impacting body, and the exact sequence of events that followed in the immediate aftermath. The evidence supporting this theory comes from lunar samples brought back by Apollo missions, which reveal isotopic ratios remarkably similar to Earth's composition, suggesting a common origin. Yet the models that attempt to reconstruct this impact require assumptions about planetary densities, rotation rates, and impact angles that cannot be directly verified and remain subject to substantial scientific debate. Additional mysteries surrounding lunar formation include the question of how the Moon achieved its current orbital distance, and why its formation appears to have been so efficient in terms of angular momentum transfer, as well as uncertainties about whether the Moon formed from a single giant impact or potentially from multiple smaller collisions that occurred over an extended period. The psychological mechanism driving our fascination with this particular mystery seems rooted in humanity's fundamental desire to understand our place in the cosmos, to trace the origins of the object that has captivated our species throughout history, and to reconstruct events so ancient and catastrophic that they exist beyond the realm of direct observation. We have normalized our acceptance of the giant impact theory despite its unresolved complications, because it provides an elegant explanatory framework that accounts for most observable phenomena. Yet this normalization masks the profound gaps in our understanding and the considerable scientific humility required when confronting events from Earth's deep past. Future missions to the Moon, including sample returns from the far side and subsurface drilling expeditions, promise to refine our understanding by providing access to lunar material untouched by the massive impacts that have reshaped the near side, potentially revealing whether the isotopic signatures we currently rely upon truly represent the primordial Moon or merely reflect post-formation mixing and differentiation processes that have obscured the original compositional record. For decades, Mars has captivated our scientific imagination as a world that might once have hosted liquid water flowing across its ancient surface, carving vast networks of valleys and canyons that we can still observe today through our orbital telescopes and rovers. Yet despite overwhelming evidence of water's historical presence on the red planet, we remain profoundly uncertain about where that water went, how much existed at its peak, and whether any substantial liquid reserves persist beneath the Martian surface in the present day. The evidence itself is compelling and multifaceted. Satellite imagery reveals channel systems and delta formations that appear identical to river deltas found on Earth. Mineral compositions suggest chemical weathering patterns consistent with water interaction, and spectroscopic analysis has detected hydrated minerals locked within ancient rocks, all pointing toward a wetter, warmer Mars that existed billions of years ago during a period when the planet possessed a thicker atmosphere and stronger magnetic field capable of protecting surface water from solar radiation and cosmic erosion. Yet the mystery deepens when we consider the mechanism of loss, for Mars somehow transitioned from this water-rich state to the arid desert we observe now, a transformation so complete that tracking where the water went has become one of planetary science's most vexing questions, with theories ranging from atmospheric escape into space, to percolation deep into underground aquifers, to chemical incorporation into subsurface minerals, none of which can fully account for the magnitude of water that appears to have vanished. What makes this mystery particularly difficult to accept despite our technological sophistication is that we cannot definitively answer it even with rovers on the surface and satellites circling overhead, revealing a humbling gap between our observational capabilities and our actual understanding of planetary processes, and we have become accustomed to this state of incomplete knowledge. Accepting that some of the most fundamental questions about our neighboring world remain suspended in scientific uncertainty, neither solved nor abandoned, but perpetually investigated through incremental discoveries that suggest answers without confirming them. Recent discoveries have intensified this investigation. NASA's rovers have detected seasonal methane fluctuations that might indicate subsurface microbial activity or geological processes involving trapped water, while orbital instruments have mapped extensive deposits of water ice in polar regions and beneath the surface, suggesting that Mars retains more frozen water than we initially calculated. Yet even these findings raise further questions rather than providing closure. For understanding whether Mars's water vanished, Venus presents one of the most perplexing puzzles in planetary science, a world that seems to have undergone a dramatic and catastrophic transformation from conditions that might have once resembled those of early Earth to the hellish inferno we observe today, where surface temperatures exceed 460 degrees Celsius and atmospheric pressures crush with the force of being deep beneath Earth's oceans. The mystery that haunts planetary scientists is this fundamental question of what Venus was like billions of years ago, and how it could have possibly transitioned from what evidence suggests might have been a temperate, possibly habitable world with liquid water oceans to the barren, scorched planet locked in a runaway greenhouse effect that we see now. The mechanism driving this transformation appears to involve a catastrophic positive feedback loop centered around water and carbon dioxide in Venus's atmosphere, a process that scientists believe may have been triggered by the planet's proximity to the Sun, which delivered relentless solar radiation that gradually increased surface temperatures over millions of years. As the planet warmed, water in the oceans evaporated into the upper atmosphere, where ultraviolet radiation from the Sun could break apart these water molecules, allowing hydrogen to escape to space, while oxygen remained to chemically interact with surface rocks, fundamentally stripping Venus of the water that once covered it. Simultaneously, volcanic outgassing released vast quantities of carbon dioxide into the atmosphere, and without water oceans to absorb and cycle this carbon dioxide through chemical weathering processes, the greenhouse effect intensified catastrophically, creating a vicious cycle where rising temperatures drove more evaporation, more atmospheric loss, and ever-increasing surface heat. What persists as genuinely mysterious despite our understanding of these broad mechanisms is the precise timeline and initial conditions that set this process in motion. The exact role that Venus's size and internal geology played in determining its fate differently from Earth, and whether Venus truly did harbor oceans and possibly even life before this transformation occurred. A question that remains frustratingly unanswered as we continue to study this enigmatic world and consider what it might teach us about planetary habitability and the fragility of clement climates throughout the cosmos. Recent missions to Venus, including orbital surveys that have detected possible signatures of past water vapor and ongoing volcanic activity, suggest that the planet's transformation may have occurred more rapidly than once believed, potentially within just a few 100 million years rather than over billions, a timeline that makes Venus not merely a historical curiosity but. When the New Horizons spacecraft flew past Pluto in July of 2015, it revealed something that would captivate scientists and the public imagination alike. A massive, heart-shaped feature spanning roughly 1,300 kilometers across the dwarf planet's surface, a formation so distinctive that it immediately became known as Pluto's heart. The western lobe of this heart, a region called Tombo Regio, is filled with nitrogen ice, methane ice, and carbon monoxide ice, creating a vast smooth expanse that contrasts starkly with the cratered, ancient terrain surrounding it. The eastern lobe contains more varied terrain with elevated ridges and scarps, while the entire structure sits in a basin that appears to have been formed by some cataclysmic impact billions of years ago. Despite decades of astronomical study and theoretical modeling, the precise mechanisms by which this iconic feature formed and continues to maintain its distinctive shape remain largely unexplained, representing one of the solar system's most puzzling geological formations. Scientists understand that the smooth, icy plains within the heart's western lobe are actively changing, with slow-moving glaciers of frozen nitrogen flowing like terrestrial rivers of ice. Yet the fundamental question of how such an enormous, geometrically distinctive formation could emerge on such a small celestial body through ordinary geological processes remains contentious and inadequately resolved. The leading hypotheses suggest that the basin may have originated from a massive collision early in Pluto's history, but modeling suggests that the impact should have either completely obliterated the region or created a far different topography than what we observe. Furthermore, the remarkable symmetry and depth of the heart structure seems inconsistent with simple impact crater mechanics, leading researchers to propose that subsequent geological processes, possibly involving subsurface water or cryovolcanism, may have reshaped the original impact basin into its present form. Yet each proposed mechanism introduces new complications and requires fine-tuned conditions that seem improbably specific for such a distant, geologically modest world, and despite computational models and comparative analysis with impact craters on other bodies, no consensus explanation has emerged that satisfactorily accounts for all observed characteristics of Pluto's heart. What makes this mystery particularly intriguing is that Pluto's heart challenges our fundamental understanding of how small bodies in the outer solar system evolve, suggesting that processes we consider exotic or rare elsewhere may be commonplace on worlds we have only recently begun to understand.